Imagine a journey not just across vast distances of space, but through time itself. Picture soaring past galaxies millions of light years away, as if they were mere stepping stones, or perhaps witnessing the birth of stars long extinguished, or even civilizations yet to rise. This isn't just the stuff of science fiction blockbusters like Interstellar, where characters navigate cosmic shortcuts to save humanity. This is the tantalizing, deeply complex, and utterly mind-bending realm of wormholes, and the very real, albeit theoretical, possibility of space-time travel. For centuries, humanity has gazed at the stars, dreaming of transcending the seemingly insurmountable barriers of distance and time. We've wondered if there are pathways, hidden tunnels in the fabric of the universe that could whisk us from one cosmic doorstep to another in the blink of an eye, or perhaps even take us back to a pivotal moment in history or forward into a distant future. The concept of a wormhole, sometimes called an Einstein-Rosen bridge, isn't just a fantastical notion for a Hollywood script. It's a theoretical construct arising directly from Albert Einstein's equations of general relativity. These cosmic shortcuts, if they exist, would be like ephemeral tunnels connecting two distinct points in space-time, potentially light years apart, or even linking different universes or different moments in time within our own. They challenge our most fundamental understanding of reality, pushing the boundaries of what we believe is possible and stirring a profound sense of awe and wonder within us. The very idea suggests a universe far more intricate and mysterious than we currently comprehend, a cosmos riddled with secret passages just waiting to be discovered. So buckle up, aspiring cosmic adventurers, because today we're embarking on an extraordinary intellectual odyssey. We're going to dive deep into the 30 most fascinating, perplexing, and sometimes unsettling theories about wormholes and space-time travel. From the theoretical physics that underpins their existence to the paradoxical implications of journeying through time, we'll explore what scientists, philosophers, and even dreamers have envisioned. We will unravel concepts that sound like they belong in a parallel dimension, yet they emerge from serious scientific inquiry into the very nature of gravity, causality, and the universe's ultimate secrets. Get ready to question everything you thought you knew about dimensions, distance, and destiny, as we unlock the mysteries that could one day redefine our place in the cosmos. Our cosmic journey begins with the very genesis of the wormhole concept, a brilliant and somewhat unexpected byproduct of Albert Einstein's groundbreaking work. Back in 1935, Einstein, along with his colleague Nathan Rosen, was exploring the mathematical intricacies of general relativity, a theory that describes gravity not as a force, but as a curvature in the fabric of space-time caused by mass and energy. In their pursuit of a unified theory that could link gravity with electromagnetism, they stumbled upon a peculiar solution within these equations. It wasn't a solution that described the universe we see around us, but rather a theoretical gateway, a kind of tunnel through space-time that could connect two distant points. They called this theoretical construct an Einstein-Rosen bridge, a term that has since become synonymous with what we popularly know as a wormhole. Imagine their discovery like finding an unexpected shortcut hidden within a complex map. The equations suggested that instead of traversing the vast, curved expanse between 2 points, a path could exist that effectively folds space-time, bringing those points together almost instantaneously. What did this theoretical bridge look like? Well, the concept describes two mouths, entry and exit points connected by a narrow throat. Picture it like two funnels whose narrow ends are joined together, forming a passage that bypasses the long journey across the funnel's wide mouth. So, instead of traveling millions of light years across the universe to reach a distant star, you might theoretically enter a wormhole's mouth, traverse its short throat, and emerge from the other mouth at your destination in a fraction of the time. This vision of cosmic shortcuts was revolutionary, offering a tantalizing glimpse into possibilities that defied all conventional understanding of interstellar travel. However, despite the initial excitement surrounding this theoretical marvel, Einstein and Rosen's original model presented significant challenges. These early wormholes, as described by their calculations, were inherently unstable. Think of trying to hold open a tunnel made of rubber bands. Any slight disturbance, even the smallest bit of matter or energy passing through, would cause it to snap shut almost immediately. This instability meant that any attempt to send anything, even a single photon of light, through such a wormhole would cause it to collapse before it could complete its journey. Furthermore, these original Einstein-Rosen bridges were not traversable in the way we might imagine for space-time travel. They were more like mathematical curiosities, non-dynamic connections that could not be kept open long enough for anything to actually pass from one side to the other. They were static solutions, meaning they didn't allow for the flow of time or even the movement of objects through them. So, while they offered the first theoretical inklings of wormholes, they quickly proved to be dead ends for practical application in space-time navigation, initiating a long scientific quest to find ways to stabilize these elusive cosmic tunnels. The realization that Einstein and Rosen's initial wormholes were impractical spurred physicists to search for a more viable solution. This quest led to a monumental breakthrough in 1988, when the brilliant theoretical physicist Kip Thorne, alongside his student Michael Morris, unveiled a revolutionary concept, the traversable wormhole. Their groundbreaking work wasn't just a theoretical exercise. It emerged from a very practical question posed by none other than world-renowned astronomer Carl Sagan. Sagan, writing his science fiction novel Contact, faced a dilemma. How could his protagonist realistically travel vast interstellar distances? He turned to Thorne for scientific accuracy, and what followed reshaped the understanding of wormholes. Thorne and Morris recognized the critical flaw in the earlier models: instability. The solution, they theorized, lay not in modifying the wormhole structure, but in introducing a hypothetical substance known as exotic matter. Now, when we talk about exotic matter, don't picture some glowing, fantastical goo from a sci-fi movie. In physics, exotic refers to something that possesses properties unlike ordinary matter. The key property for wormhole stability is negative energy density. Imagine ordinary matter like a planet or a star warping space-time by creating a gravitational pull, represented as a downward curve like a bowling ball on a stretched rubber sheet. Exotic matter, on the other hand, would do the opposite. It would exert a gravitational push, causing space-time to curve outwards or flare open. This outward push is precisely what would be needed to counteract the immense gravitational forces that cause a wormhole's throat to collapse, effectively propping it open long enough for something or someone to pass through. Think of it like this: if ordinary matter tries to pinch the wormhole shut, exotic matter acts as a kind of anti-gravity scaffolding, actively holding the throat of the wormhole open. This extraordinary concept provided the first theoretical mechanism for a stable, traversable wormhole. Without this exotic matter, the very act of passing through would almost instantly cause the wormhole to snap shut, crushing anything inside. With it, however, a stable pathway could in theory be maintained, allowing for instantaneous travel across cosmic distances. The Morris-Thorne wormhole wasn't just a mathematical construct. It offered a glimmer of hope that these cosmic shortcuts might one day be more than just theoretical curiosities, pushing the boundaries of what was once considered impossible into the realm of the theoretically plausible. While the concept of traversable wormholes opened up incredible possibilities for interstellar travel, it simultaneously unveiled an even more mind-bending implication: the potential for time travel. This isn't just a byproduct, it's an inherent consequence of how wormholes interact with the fabric of space-time, particularly when combined with the principles of Einstein's special and general relativity. The key lies in manipulating the mouths of these theoretical tunnels. Imagine if you could take one mouth of a stable wormhole and accelerate it to nearly the speed of light, leaving the other mouth stationary relative to some distant point. According to special relativity, time would pass more slowly for the accelerated mouth compared to its stationary twin. This phenomenon, known as time dilation, means that if you were to enter the stationary mouth and exit the accelerated one, you would emerge into the future of your starting point. Alternatively, consider placing one wormhole mouth very close to a massive object like a black hole where gravity is incredibly strong. General relativity tells us that powerful gravitational fields also warp time, slowing it down significantly. So, the mouth near the black hole would experience time passing at a much slower rate than its counterpart far away in weaker gravity. If you were to enter the mouth far from the black hole and exit the one nearby, you would again find yourself traveling into the future relative to your original timeline. Conversely, entering the wormhole at the mouth near the black hole and exiting the distant one would effectively send you into the past of the distant mouth's timeline, creating a potential pathway for backward time travel. To illustrate this effect, consider the famous twin paradox. Imagine two identical twins. One twin, let's call her Alice, stays on Earth. The other twin, Bob, embarks on a journey in a spaceship traveling at a significant fraction of the speed of light. When Bob returns to Earth after what feels like a few years to him, he would find that Alice, who remained on Earth, has aged much more. Perhaps decades have passed for her while only a few years passed for Bob. This isn't just science fiction, it's a verifiable consequence of special relativity confirmed by experiments with atomic clocks. Now apply this to a wormhole. If one mouth of the wormhole were to undergo this same high-speed journey or be placed in a strong gravitational field, the time dilation experienced by that mouth would effectively create a time difference between the two ends of the wormhole. Stepping through such a wormhole would not only transport you through space but also through time, bridging different moments in history. The implications of such a capability are profound and frankly mind-boggling. The ability to travel into the past, even theoretically, immediately raises the specter of causality paradoxes. If you could go back in time, what would stop you from altering events that led to your own existence? This is the classic grandfather paradox, where one might prevent their own birth, leading to a logical contradiction. Or imagine the butterfly effect, where a seemingly insignificant alteration in the past could lead to drastically different future outcomes. These are not just philosophical musings, they are serious challenges that physicists grapple with when considering the implications of traversable wormholes as time machines. While the equations allow for these possibilities, the universe itself might have built-in safeguards or unknown physical principles that prevent such paradoxes from actually occurring. This brings us to the very edge of our understanding, where physics meets philosophy, and the laws of the universe might be even stranger than we can currently imagine. Given the profound challenges posed by time travel paradoxes and the elusive nature of exotic matter, physicists continue to explore alternative, equally mind-bending ideas about wormholes. One of the most fascinating and revolutionary theories to emerge in recent years doesn't just push the boundaries of our understanding of space-time. It attempts to bridge the two great pillars of modern physics: general relativity, which describes the universe on a grand scale, and quantum mechanics, which governs the subatomic world. This bold hypothesis, proposed in 2013 by theoretical physicists Juan Maldacena and Leonard Susskind, suggests a deeply interconnected relationship between wormholes, or Einstein-Rosen bridges, and quantum entanglement. Their provocative idea, often summarized by the elegant equation ER equals EPR, posits that entanglement might actually be equivalent to a wormhole. Let's break down what that means. Einstein-Rosen bridges, as we've discussed, are those theoretical shortcuts through space-time. EPA, on the other hand, refers to the Einstein-Podolsky-Rosen paradox, a thought experiment that highlights one of the most baffling phenomena in quantum mechanics: entanglement. Imagine two particles born together or having once interacted that become intrinsically linked. If you measure a property of one particle, say its spin, the other entangled particle, no matter how far away it is in the universe, instantaneously exhibits a correlated property. It's as if they're communicating faster than the speed of light, a concept Einstein famously called spooky action at a distance. This instantaneous connection has puzzled scientists for decades, seemingly violating our classical understanding of reality. Maldacena and Suskind's radical proposal suggests that this spooky action at a distance isn't spooky at all, but rather a manifestation of a microscopic wormhole connecting the entangled particles. In their model, the act of two particles becoming entangled is akin to a tiny, non-traversable wormhole forming between them. This isn't a wormhole you can send spaceships through, or even signals, but a fundamental geometric connection built into the fabric of space-time at the quantum level. The idea is that the quantum information of the entangled particles travels through this microscopic wormhole, creating that instantaneous correlation we observe. So, instead of information teleporting across vast distances, it's actually taking a shortcut through a tiny quantum wormhole. This theory offers a tantalizing path toward unifying general relativity and quantum mechanics, two fields that have famously resisted combination. General relativity excels at describing gravity and the large-scale structure of the cosmos, but it breaks down at extremely small scales, like inside a black hole or at the moment of the Big Bang. Quantum mechanics, conversely, perfectly describes the behavior of particles at these tiny scales but struggles to incorporate gravity. The ER equals EPR hypothesis suggests that the geometric nature of space-time, central to general relativity, is deeply intertwined with the quantum phenomenon of entanglement. If true, it could mean that the very fabric of space-time itself emerges from the collective properties of entangled particles, providing a potential framework for a quantum theory of gravity. It's a profound thought. The universe might be knitted together by an intricate web of these tiny, unobservable wormholes, linking every piece of matter and energy in a cosmic dance of quantum connections. This perspective radically reshapes our understanding of reality, hinting that the spooky action at a distance isn't a magical force, but a tangible, albeit microscopic, bridge. Beyond the theoretical bridges connecting distant particles or future timelines, some physicists propose an even more astonishing origin for wormholes, the very beginning of the universe. This brings us to a fascinating concept known as primordial wormholes, microscopic tunnels that might have spontaneously formed during the incredibly energetic and chaotic aftermath of the Big Bang. Imagine the early universe not as a smooth, uniform expanse, but as a frothing, bubbling cauldron of energy and space-time, undergoing extreme fluctuations on scales smaller than atoms. In this violent, super-dense environment where quantum effects reign supreme, the very fabric of space-time could have been warped and distorted in ways almost unimaginable today. The conditions during the universe's infancy were so extreme that brief, transient wormholes might have popped into existence, then vanished in a flicker, much like virtual particles that appear and disappear constantly in empty space. However, theory suggests that some of these microscopic wormholes, if they possessed certain properties like negative mass or tension, might have survived this tumultuous period. This idea leans heavily on quantum gravity, a field that attempts to reconcile general relativity with quantum mechanics. If space-time itself is quantized, meaning it exists in discrete, tiny units, then at the smallest scales, it might resemble a quantum foam, a turbulent sea of fluctuating mini-wormholes and other exotic geometries. Within this foam, some of these wormholes might have been frozen or stabilized as the universe expanded and cooled, remnants of a time when the very laws of physics were still solidifying. The implications of surviving primordial wormholes are truly profound. If they exist, where are they now, and what form would they take? One intriguing possibility is that these ancient cosmic relics could contribute to the mysterious dark matter that astronomers believe makes up about 27% of the universe. Dark matter doesn't interact with light or other forms of electromagnetic radiation, making it invisible to our telescopes, yet its gravitational effects are clearly observed in the rotation of galaxies and the clustering of galaxy clusters. If primordial wormholes were sufficiently small and numerous, they could exert gravitational influence without emitting or absorbing light, fitting the description of dark matter candidates. They wouldn't be large enough for anything to travel through them in a conventional sense. Instead, they would be like tiny gravitational anomalies embedded within the fabric of space-time, exerting their pull from the shadows. Another aspect of this theory suggests that these microscopic wormholes, if stable, could act as tiny, localized distortions in space-time that could affect quantum processes. While not traversable, their very presence could leave subtle imprints on the universe, perhaps influencing the distribution of matter or even having effects on quantum entanglement across vast distances. Proving their existence, however, remains one of the greatest challenges in physics. Detecting something that is both microscopic and potentially invisible, a relic from the first fractions of a second after the Big Bang, would require technologies and theoretical frameworks far beyond our current capabilities. Yet the concept itself opens up a breathtaking vista of possibilities, suggesting that the universe might be riddled with ancient, unseen shortcuts, silently influencing its evolution since the dawn of time, waiting to be subtly uncovered through ever more precise measurements of the cosmos. While primordial wormholes represent a potential relic of the universe's fiery birth, other theories connect wormholes to some of the most enigmatic objects in the cosmos, black holes. This brings us to a fascinating and deeply speculative concept, the possibility that wormholes might be intrinsically linked to or even manifest as white holes. If the very mention of a white hole sounds like something out of a theoretical physicist's fever dream, that's because in many ways it is the purest form of scientific speculation. White holes are in essence the time-reversed counterparts of black holes. To understand this, let's briefly revisit black holes. We know black holes are cosmic devourers, regions of space-time where gravity is so intense that nothing, not even light, can escape once it crosses a boundary called the event horizon. They are characterized by a singularity at their center, a point of infinite density. Now imagine running the film of a black hole in reverse. Instead of matter falling in, a white hole would be a region of space-time from which matter and light can only escape and nothing can enter. Just as a black hole draws everything inward, a white hole would violently expel everything outward. Its event horizon would act like a one-way door, but in the opposite direction. Everything inside can get out, but nothing from the outside can get in. The connection to wormholes emerges from certain solutions within Einstein's general relativity equations. Some mathematical models of black holes, particularly non-rotating ones, suggest that beyond the singularity, there might exist another universe or another region of our own universe accessible through a bridge. This theoretical bridge, often depicted as a tunnel connecting the interior of a black hole to a white hole, is precisely where the wormhole concept intertwines. In this view, a black hole acts as an entrance to a wormhole, and a white hole acts as the exit. So, if you were to fall into a black hole instead of being crushed at the singularity, some theories propose you might emerge from a white hole somewhere else, or perhaps somewhere else in the cosmos. This idea is incredibly alluring because it offers a potential mechanism for matter and energy to traverse vast cosmic distances, or even for new universes to be born from the collapse of matter in another. For instance, some cosmologists have toyed with the concept that our own universe might have emerged from a white hole that formed as the exit point of a black hole in a parent universe. This would elegantly explain why the Big Bang appears to have started from a singularity, a point where all matter and energy in our universe were compressed into an incredibly small volume, which then rapidly expanded. Instead of a random cosmic explosion, it would be a continuous process of new universes budding off from older ones through these cosmic umbilical cords. However, despite their elegant theoretical symmetry with black holes, there's a crucial distinction. White holes have never been observed, nor is there any direct evidence for their existence. While black holes are routinely detected by their gravitational effects on surrounding matter, white holes remain purely theoretical constructs. The laws of physics, as we currently understand them, also present significant challenges to their formation and stability. It's difficult to imagine how a white hole could naturally arise in the universe, as it would require a highly improbable fine-tuning of initial conditions. Furthermore, the very idea of matter being continuously ejected from a white hole would mean that it would have to be in a constant state of expulsion, something that seems to defy the ordinary flow of time and entropy. Nevertheless, the possibility remains a captivating area of theoretical exploration. If white holes do exist, and if they are indeed the exit points of wormholes, their observable signatures would be quite dramatic. We would expect to see massive bursts of energy and matter erupting from seemingly empty regions of space, defying conventional astrophysical explanations. Such an observation would present a monumental challenge to our current understanding of the universe, providing direct evidence for these time-reversed cosmic fountains and, by extension, the wormholes that connect them. While highly speculative, the idea of black holes leading to white holes via wormholes paints a complete, albeit fantastical, picture of cosmic recycling and interconnectedness, where the ultimate devourers of matter are also the ultimate birthers of new phenomena. While the concept of white holes stemming from black holes offers a potential macroscopic connection for wormholes, another incredibly ambitious theory dives even deeper into the fundamental nature of reality, proposing that wormholes might be a natural consequence of the universe having more than the 4 dimensions we perceive. This brings us to the fascinating, enigmatic, and often mind-bending realm of string theory. String theory is one of the leading contenders for a theory of everything, a unified framework that seeks to reconcile general relativity with quantum mechanics by positing that the fundamental building blocks of our universe aren't point-like particles, but rather tiny, vibrating strings. These strings, depending on how they vibrate, give rise to all the particles and forces we observe, from electrons and photons to gravity itself. One of the most striking predictions of string theory is the existence of extra spatial dimensions beyond the familiar 3 up-down, left-right, forward-backward, and 1 of time. These extra dimensions aren't immediately apparent to us because, according to the theory, they are compactified or curled up into incredibly tiny spaces, too small to be directly detected by our current instruments. Imagine a garden hose from a distance. It looks like a one-dimensional line, but up close you see it has a second, curled-up dimension around its circumference. In a similar way, string theory suggests that at every point in our familiar 3 dimensions, there are these tiny, curled-up extra dimensions. Now, how do these extra dimensions relate to wormholes? This is where the landscape of possibilities expands dramatically. If space-time isn't merely 4-dimensional, but contains these hidden, higher dimensions, then what we perceive as long distances in our familiar 3 dimensions might actually be very short distances when traversed through one of these extra dimensions. Think of it like this. Imagine 2 points on a sheet of paper. The shortest distance between them is a straight line across the paper. But if you fold the paper, those 2 points might now be directly on top of each other, and a path could exist that goes through the folded dimension, essentially a shortcut. In string theory, a wormhole might not be a tunnel through our 3 spatial dimensions, but rather a shortcut that exploits these higher, curled-up dimensions. The implications are profound. This could mean that what appears to be a vast, empty expanse between two galaxies in our three-dimensional view is actually a much shorter path in an underlying higher dimensional geometry. A journey that would take millions of light years in our conventional space-time might be traversable in mere moments by somehow accessing and moving through one of these extra dimensions. Theorists like the aforementioned Leonard Susskind have extensively explored how such higher dimensional shortcuts might manifest as wormholes. In this framework, the wormhole isn't just a folding of our familiar space-time. It's a direct consequence of the universe's inherent higher dimensional structure. It's as if the universe has built-in express lanes that operate outside our usual perception of distance. Furthermore, string theory offers potential mechanisms for the stability of these wormholes, possibly bypassing the need for exotic matter. The very nature of these curled-up dimensions and the unique properties of strings vibrating within them could naturally give rise to geometries that are inherently stable and traversable. The idea is that the strings themselves and their interactions across these extra dimensions could effectively prop open the wormholes, preventing their collapse. This moves the challenge from finding an elusive substance like exotic matter to understanding the fundamental structure of reality at its most basic level. If string theory proves to be correct, then wormholes might not be theoretical curiosities requiring impossible conditions, but rather an intrinsic feature of our multi-dimensional universe, perhaps even forming part of the cosmic architecture that connects distant regions or even different universes within the multiverse concept that string theory also supports. The search for wormholes in this context becomes a search for the subtle imprints of these hidden dimensions on our observable universe, a quest for the true multi-dimensional pathways that might connect us to the far reaches of existence. While string theory suggests wormholes might be a natural consequence of higher dimensions, another incredibly profound and equally mind-bending concept known as the holographic principle offers a completely different yet equally compelling perspective on these cosmic shortcuts. This theory posits that our three-dimensional universe, with all its galaxies, stars, and even us, might actually be a holographic projection of information encoded on a distant, two-dimensional surface. Think of it like a cosmic hologram where the universe we experience is merely an illusion, a detailed projection from a flat, boundary surface. This radical idea gained significant traction with a concept called the anti-de Sitter space/conformal field theory correspondence, or ADS/CFT correspondence for short. It's a highly mathematical conjecture that connects two seemingly disparate areas of physics: gravity in a specific type of space called anti-de Sitter ADS space, which is negatively curved like a saddle, and quantum field theories without gravity that lie on the boundary of that space, known as conformal field theories CFT. What makes this correspondence so revolutionary is that it acts like a dictionary, allowing physicists to translate problems from one side to the other. For instance, a complex problem involving gravity in the higher dimensional ADS space might have a much simpler, equivalent description in the lower dimensional CFT living on its boundary. Now, here's where wormholes enter this picture in a spectacular way. Within this holographic framework, physicists have discovered that certain patterns of quantum entanglement on the two-dimensional boundary theory correspond directly to the presence of wormholes in the higher dimensional anti-de Sitter space. To put it simply, if you have two regions of the boundary theory that are highly quantum entangled, the holographic principle suggests that these entangled regions are connected by a wormhole in the bulk, the higher dimensional space. This connection became particularly exciting when it was shown that this applies even to quantum teleportation. What appears as instantaneous information transfer via quantum entanglement on the boundary might actually be described as information traveling through a wormhole in the bulk. This is not a traversable wormhole in the sense that a spaceship could fly through it to journey across vast cosmic distances. Instead, it's a conceptual wormhole, a geometric representation of quantum entanglement itself. It suggests a deep and fundamental relationship between the geometry of space-time and the quantum information encoded within it. The more entangled two regions are, the shorter or more direct the wormhole connection between them. This implies that the very fabric of space-time, including wormholes, might not be a fundamental entity but rather an emergent property arising from the intricate dance of quantum information. The implications for our understanding of a holographic universe are profound. If entanglement is equivalent to a wormhole, then the spooky action at a distance that so puzzled Einstein might literally be a shortcut through an underlying space-time geometry. Furthermore, this provides a powerful new tool to study the mysteries of quantum gravity. By examining the behavior of entangled quantum systems on a two-dimensional surface, physicists can gain insights into the properties of black holes and wormholes in higher dimensions, something that is incredibly difficult to do directly. It suggests that the universe might be performing a cosmic magic trick, projecting its three-dimensional reality from a two-dimensional stage. Instead of being a solid, three-dimensional entity, our universe could be seen as a grand illusion, a projection where distance and connectivity are fundamentally interwoven with quantum information and entanglement. This framework hints that the answer to some of the universe's biggest puzzles might lie in understanding how quantum information on a flat surface gives rise to the curved, dynamic space-time we inhabit, including the bizarre and beautiful phenomena of wormholes. While the holographic principle suggests wormholes are deeply tied to quantum entanglement, another highly speculative yet compelling idea delves into the relationship between wormholes and one of the universe's most profound mysteries, dark energy. This concept proposes that the exotic matter needed to stabilize traversable wormholes, with its bizarre property of negative energy density, might be intimately linked to the very force driving the accelerated expansion of the cosmos. To understand this connection, let's briefly touch upon dark energy. For decades, astronomers believed the universe's expansion, set in motion by the Big Bang, was gradually slowing down due to the gravitational pull of all the matter within it. However, in the late 1990s, observations of distant supernova revealed a shocking truth. The universe isn't just expanding, its expansion is actually accelerating. This acceleration requires a mysterious force, an unknown form of energy with repulsive gravity, essentially pushing everything apart. This unseen, unmeasurable force is what we've dubbed dark energy. It's estimated to make up about 68% of the total energy density of the universe, dwarfing ordinary matter and dark matter combined. Its nature remains one of the biggest unanswered questions in cosmology. Now consider the requirements for a traversable wormhole. As we discussed, Kip Thorne and others realized you need exotic matter, a substance with negative energy density, to counteract the wormhole's tendency to collapse. This negative energy density is precisely what would exert a repulsive gravitational effect, propping the wormhole open. This sounds strikingly similar to the properties attributed to dark energy. Could the exotic matter required for a wormhole be a localized manifestation of dark energy, or perhaps share a common origin with it? Some theoretical physicists speculate that if dark energy permeates the entire universe, subtly pushing it apart on cosmic scales, then perhaps concentrated pockets of this negative energy could be harnessed to stabilize a wormhole in a much more localized and powerful way. Imagine a scenario where the universe's pervasive dark energy isn't just a uniform background field, but can somehow be manipulated or even compressed to create the intense negative pressure needed within a wormhole's throat. This would mean that the very force expanding the universe on a grand scale could, in principle, be the same fundamental phenomenon that creates shortcuts through space-time on a smaller, localized scale. This theoretical link is appealing because it seeks to explain two of the most puzzling phenomena in modern physics, dark energy and stable wormholes, with a single underlying concept. It suggests that if we ever manage to understand and control dark energy, we might simultaneously unlock the secrets to creating and maintaining traversable wormholes. However, the challenges are immense. Our current understanding of dark energy is rudimentary at best. We observe its effects, but we have no idea what it actually is, how it works, or whether it can be localized or manipulated in any way. Furthermore, the amount of negative energy density required to hold open a macroscopic, human traversable wormhole would be astronomical, far exceeding anything we can currently conceive of generating or controlling. It would be like trying to bottle up the force expanding the entire universe into a tiny, stable tunnel. The energy requirements are mind-boggling, effectively placing this concept firmly in the realm of advanced theoretical physics, far from any practical application. Nevertheless, linking wormholes to dark energy offers a tantalizing theoretical avenue. It suggests that the quest for space-time travel might not be about inventing entirely new forms of matter, but rather about understanding and harnessing a fundamental, pervasive component of our universe that is already at play on the grandest cosmic scales. It paints a picture of a universe where the forces shaping its destiny on scales of billions of light years are also the keys to unlocking shortcuts across mere millions, a profound and elegant connection that could redefine our place within its accelerating expanse. While many theories link wormholes to the universe's grandest forces and hidden dimensions, another highly compelling and scientifically rigorous area of exploration suggests wormholes could be hiding in plain sight, masquerading as something else entirely: black holes. This theory challenges the conventional understanding of black holes as mere gravitational singularities, proposing instead that some, or perhaps even all, black holes might actually conceal wormhole interiors, offering a radical alternative to the notion of infinite density. Let's first remember what we usually understand a black hole to be. According to general relativity, when a massive star collapses under its own gravity, it forms a region of space-time where gravity is so strong that nothing, not even light, can escape once it crosses the event horizon. At the very center of this black hole is believed to lie a singularity, a point of infinite density and zero volume, where the laws of physics as we know them break down. This concept, however, presents numerous theoretical challenges, not least of which is the information paradox. The information paradox asks what happens to the quantum information of matter that falls into a black hole. Quantum mechanics states that information can never be truly destroyed, yet if it falls into a singularity, it seems to vanish from the universe, leading to a fundamental contradiction between general relativity and quantum mechanics. This is where the idea of wormholes providing an alternative to the singularity becomes incredibly attractive. Theoretical models, particularly those incorporating quantum gravity effects, suggest that instead of collapsing to an infinitely dense point, the extreme gravitational forces might instead cause space-time to fold in on itself, forming a stable, non-singular wormhole at the center. In this view, what we perceive as the event horizon of a black hole could actually be the mouth of a traversable wormhole. Instead of leading to a destructive singularity, falling into such a black hole might simply lead to the throat of a wormhole, potentially connecting to another region of space-time, another universe, or even another point in our own universe. This concept is sometimes referred to as a regular black hole or a non-singular black hole, implying that the black hole's interior is not a point of infinite density but a finite, if incredibly extreme, region. The implications for the information paradox are profound. If a black hole contains a wormhole instead of a singularity, then the information of anything that falls in wouldn't be destroyed. It would simply travel through the wormhole to emerge somewhere else. This somewhere else could be a white hole in another part of the universe, as we discussed previously, or another baby universe entirely. The information would be preserved, just relocated through a cosmic shortcut, thereby resolving the paradox. It's a much more elegant solution than simply having information disappear from existence. which violates a fundamental tenet of quantum mechanics known as unitarity. Furthermore, these theoretical models often involve concepts like gravastars or fuzzballs, which are alternatives to black holes that avoid singularities. A gravastar, for instance, is a hypothetical object where, instead of a singularity, there's a core of exotic matter that prevents collapse, surrounded by a shell of ordinary matter and an event horizon-like boundary. The core could theoretically be a wormhole. Similarly, string theory suggests that black holes might not be empty space with a singularity, but rather fuzzballs, which are complex quantum mechanical structures made of vibrating strings that effectively smear out the singularity and the event horizon. Within these fuzzball models, wormhole-like connections could naturally emerge as part of their intricate internal geometry. While these models offer a tantalizing resolution to the information paradox and avoid the problematic singularity, they too come with their own set of challenges. They often require the presence of exotic matter or rely on quantum gravity theories that are still under development and lack experimental verification. Detecting whether a black hole truly harbors a wormhole instead of a singularity would require observations of extreme precision, probing the very nature of space-time near the event horizon. Nevertheless, the idea that black holes might be cosmic chrysalises hiding traversable wormholes is a powerful and elegant one, transforming these terrifying cosmic devourers into potential intergalactic highways and offering a compelling solution to one of physics' most enduring mysteries. This theory profoundly reconfigures our understanding of the universe's ultimate fate and its most enigmatic objects, turning destructive gravitational traps into potential gateways to new realms. While the idea of wormholes within black holes offers an elegant solution to some theoretical puzzles, the complexities deepen further when we consider the universe's more realistic black holes. Most black holes aren't static, non-rotating entities like the ones often simplified in early theoretical models. They spin, sometimes at incredible speeds, dragging the very fabric of space-time around them. This brings us to a more sophisticated description of black holes known as the Kerr metric, developed by Roy Kerr in 1963. The Kerr metric describes rotating black holes, and surprisingly, it presents an even more intriguing and potentially traversable wormhole structure. In a non-rotating black hole, the singularity is a point, but in a rotating black hole, due to the immense centrifugal forces, the singularity is stretched out into a ring, a one-dimensional circle of infinite density. This ring singularity has fascinating implications. Unlike the point singularity, which would crush anything that reaches it, the ring singularity might be avoidable. Calculations based on the Kerr metric suggest that if you were to approach a rotating black hole not directly head-on, but along a precise trajectory, you might be able to pass through the ring singularity without being destroyed. And if you successfully navigate past this ring, the equations imply you could emerge into another region of space-time through what would effectively be a wormhole. Imagine a journey into a rotating black hole. Instead of a single event horizon, the Kerr metric predicts two. The outer event horizon is the point of no return for most. But inside that, there's an inner event horizon, and between them, space-time is furiously spinning. If you manage to survive passing through both horizons and precisely navigate around the destructive ring singularity, the theory suggests that you could enter a negative energy region of space-time, a kind of anti-gravity zone, and then potentially emerge into a white hole in another part of the universe, or even into a different universe altogether. The wormhole created by a rotating black hole isn't just a tunnel, but a dynamic, swirling vortex, a cosmic merry-go-round that could whisk you away to unforeseen destinations. However, the physical plausibility of such a journey, and indeed the very existence of such traversable wormholes within rotating black holes, is a subject of intense debate among physicists. This brings us to a fundamental concept in general relativity known as cosmic censorship. The cosmic censorship hypothesis proposed by Roger Penrose essentially states that all singularities in our universe are hidden behind an event horizon. This means that if a singularity exists, it's always shielded from external observers, preventing us from ever seeing the breakdown of physics it represents. The purpose of this hypothesis is to preserve the predictive power of general relativity. If naked singularities not hidden behind an event horizon could exist, they would allow for unpredictable behaviors and a breakdown of causality, essentially making the universe nonsensical. The wormholes predicted by the Kerr metric, if traversable, challenge this hypothesis. The path around the ring singularity could potentially expose a naked singularity or violate the conditions for cosmic censorship. Furthermore, the stability of these internal wormholes is highly questionable. Any amount of matter or radiation falling into the black hole, even a tiny speck of dust, would likely destabilize the inner region, potentially causing the wormhole to collapse or the ring singularity to become a point singularity, crushing anything attempting to pass through. The fine-tuning required to navigate such a wormhole, avoiding the singularity and surviving the immense tidal forces, makes it seem virtually impossible for any physical object, let alone a human, to traverse. So, while the mathematics of the Kerr metric tantalizingly suggests the presence of ring-shaped wormholes within rotating black holes, the physical reality remains highly uncertain. The cosmic censorship hypothesis serves as a guardian of predictability in our universe, suggesting that nature forbids such easy access to singularities or pathways to other universes. Whether this hypothesis holds true, or if extreme conditions within rotating black holes could indeed allow for a loophole, remains one of the most profound unanswered questions in theoretical physics, pushing the boundaries of what might be possible at the very heart of these enigmatic cosmic giants. While the theoretical wormholes within black holes offer potential cosmic shortcuts, another fascinating and equally speculative idea shifts our focus to objects that are, in some ways, even stranger and denser than typical black holes, neutron stars. This fringe theory proposes that the cores of these ultra-compact celestial bodies might harbor tiny wormholes, formed not by the collapse into a singularity, but by the extreme conditions where matter is squeezed to its absolute limit, leading to bizarre quantum gravity effects. To appreciate this, let's briefly consider what a neutron star is. When a massive star, several times the mass of our Sun, exhausts its nuclear fuel, its core can no longer support itself against the crushing force of gravity. It collapses, triggering a spectacular supernova explosion. What's left behind is an incredibly dense remnant, typically about 1 2/10 to 2 times the mass of the Sun, but compressed into a sphere no larger than a city, perhaps 10 to 15 miles in diameter. Imagine squeezing every person on Earth into a sugar cube. That's the kind of density we're talking about. The gravitational pull at the surface of a neutron star is so immense that a single teaspoon of its material would weigh billions of tons. At these extreme densities, atomic structures collapse and electrons and protons are forced together to form a sea of neutrons, hence the name neutron star. Now, within the very heart of such a neutron star, the pressure and density reach truly unimaginable levels, far exceeding anything we can replicate even in our most powerful particle accelerators. In these extreme conditions, the classical laws of physics that govern everyday matter begin to break down, and the bizarre realm of quantum mechanics and quantum gravity begins to assert itself. It's in this hyper-dense, super-pressurized core that some theorists speculate tiny, microscopic wormholes could spontaneously form. These aren't the large, macroscopic wormholes we imagine for interstellar travel, but rather quantum-scale bridges, born from the very fabric of space-time being warped and distorted under unimaginable stress. The idea here is that at such extraordinary densities, the strong nuclear force, which usually holds atomic nuclei together, might interact with gravity in ways we don't yet fully understand. Quantum fluctuations of space-time, which are usually incredibly tiny and fleeting, could become significant enough in this extreme environment to momentarily create and sustain these miniature wormholes. These wormholes wouldn't be traversable in the conventional sense, as they would be impossibly small, perhaps just a few Planck lengths across, which is the smallest possible meaningful unit of distance in physics. Instead, they would be more akin to the primordial wormholes we discussed earlier, quantum relics of an incredibly energetic and chaotic environment. The implications of such wormholes existing within neutron star cores are speculative but fascinating. If they formed, they could potentially contribute to the star's immense density or even act as conduits for strange phenomena within its core. For instance, some theories propose that these internal wormholes could provide a mechanism for the rapid cooling of neutron stars or contribute to their extreme magnetic fields, which are billions of times stronger than Earth. They might also play a role in the exotic states of matter that are thought to exist in the deepest parts of these stars, such as quark-gluon plasma, where the fundamental building blocks of neutrons and protons are no longer confined. The presence of these quantum-scale wormholes could mean that the very geometry of space-time within a neutron star's core is far more complex and interconnected than we currently imagine, constantly fluctuating and forming tiny, ephemeral bridges. However, detecting evidence for such microscopic wormholes within neutron stars is incredibly challenging, bordering on the impossible with current technology. They would be hidden deep within the star, shielded by billions of tons of ultra-dense matter, and their effects would likely be too subtle to directly observe. Any evidence would have to come from indirect astronomical observations or highly sophisticated theoretical models that could explain some of the more puzzling behaviors of neutron stars. Nevertheless, this theory pushes the boundaries of our understanding of matter at its most extreme limits, suggesting that wormholes might not just be cosmic shortcuts, but also fundamental, quantum-level components of the most dense objects in our universe, silently influencing their internal dynamics in ways we are only beginning to ponder. It presents a captivating picture of a universe where even the most compact objects might harbor hidden, quantum doorways, bridging unimaginable pressures with unseen dimensions. While the previous theories delved into the deep physics of how wormholes might form, or how they might be linked to other cosmic phenomena, let's now pivot to perhaps the most compelling and popularly imagined application of these cosmic tunnels, their potential as ultimate interstellar shortcuts. Imagine for a moment that traversable wormholes actually exist and can be stabilized. This isn't just a slight improvement on current rocket technology. It's a revolutionary paradigm shift that would redefine our understanding of distance and fundamentally change the landscape of space exploration. The classic analogy used to explain this concept is the folding paper illustration, and it's a remarkably effective way to visualize the magic of a wormhole. Picture a vast, flat piece of paper representing the fabric of space. On one side of this paper, draw a dot representing our sun, and on the other side, mark another dot representing a distant star system, perhaps 100 light-years away. In conventional space travel, to get from our sun to that distant star, you would have to traverse the entire flat surface of the paper, covering that immense distance. Even traveling at the speed of light, it would take 100 years to reach that star. Now, instead of moving across the paper, imagine folding the paper in half, bringing the two dots, our sun and the distant star, directly on top of each other. If you could then somehow punch a hole through the folded paper, connecting the two dots directly, you would have effectively created a shortcut. That hole, bypassing the vast expanse of space, is precisely what a wormhole would do. This simple analogy elegantly illustrates how a wormhole wouldn't necessarily involve moving faster than light through conventional space. Instead, it would effectively manipulate space itself, making the distance between 2 points negligible. The journey wouldn't be about speed, it would be about topology, about bending the cosmic map to bring remote locations within immediate reach. If a stable wormhole could connect our solar system to a star system 100 light-years away, the travel time wouldn't be 100 years, but potentially minutes or even seconds, depending on the length of the wormhole's internal throat. The journey would be like stepping through a doorway from one room to another, even if those rooms were located in buildings millions of miles apart in conventional space. Let's put this into perspective with some hypothetical travel times. Consider, for example, our nearest stellar neighbor, Proxima Centauri, which is roughly 4 2/10 light-years away. With our fastest current spacecraft, like the Voyager probes, moving at about 38,000 miles per hour, it would take us roughly 77,000 years to reach Proxima Centauri. Even if we developed rockets capable of reaching 10% of the speed of light, a monumental technological leap, it would still take us 42 years. Now, if a wormhole could bridge that gap, the travel time would be reduced to perhaps mere blinks of an eye. For a journey to a star system 1,000 light-years away, which is currently an unimaginable journey of millions of years, a wormhole would collapse that timescale to something almost instantaneous. The implications are staggering. Interstellar travel, once the stuff of generations-long voyages or cryosleep, would become a daily commute, transforming humanity from a single-planet species to an interstellar civilization overnight. This radical reduction in travel time isn't just about convenience, it fundamentally changes what's possible. The resource limitations of multi-generational travel, the psychological toll on crews, and the sheer logistical nightmare of sending probes on journeys lasting millennia would vanish. We could send scientific missions to exoplanets to directly study alien life, dispatch colonization fleets to habitable worlds, and even establish trade routes across the galaxy. The energy requirements, while still massive to create and stabilize a wormhole, would be dramatically less than accelerating and decelerating a spacecraft to relativistic speeds for conventional interstellar voyages. It moves the challenge from building faster ships to engineering the very fabric of space-time. This transformational potential makes wormholes the holy grail of interstellar exploration, offering a shortcut that doesn't just shave off time but utterly rewrites the rules of cosmic engagement. While the idea of wormholes providing shortcuts within our own universe is astonishing, some of the most mind-bending theories push this concept even further, suggesting that these cosmic tunnels might not just connect distant points in our space-time, but also bridge the divide between entirely separate realities, parallel universes. This deeply speculative yet mathematically intriguing notion links wormholes directly to the multiverse hypothesis, a concept that has gained significant traction in theoretical physics and cosmology. The multiverse hypothesis posits that our universe is not the only one, but just one of an infinite number of universes, each potentially with its own set of physical laws, constants, and histories. There are several categories of multiverse theories, but when we talk about wormholes connecting them, we often lean towards what Max Tegmark, a renowned cosmologist, calls a Level 2 multiverse. In this Level 2 scenario, different universes are characterized by different physical constants, dimensions, or even different fundamental particles. Imagine a universe where gravity is stronger, or where the speed of light is different, or where there are 5 spatial dimensions instead of 3. These are not just distant regions of our own cosmos, but entirely separate cosmic bubbles that inflated from different initial conditions during the Big Bang, or perhaps even from completely separate Big Bang events. Now, how do wormholes fit into this grand cosmic tapestry? The idea is that wormholes could act as literal bridges between these distinct universes. Instead of an entrance and exit point within our universe, one mouth of the wormhole could reside in our cosmos, while the other mouth opens up into a completely different universe. This isn't just about traversing vast distances, it's about traversing fundamental differences in reality itself. If such a connection were possible, it would imply a staggering level of cosmic interconnectedness, where our universe is but one node in an infinitely vast network of realities. The wormhole wouldn't just fold space, it would fold the very fabric of existence, allowing passage between realms governed by different physical laws. Consider the immense implications of such a connection. If you could step through a wormhole into a level 2 multiverse, you might find yourself in a universe where the gravitational constant is slightly weaker, allowing planets to be much larger, or where the fine structure constant, which governs the strength of electromagnetic interactions, is different, leading to vastly altered chemistry and perhaps even entirely different forms of life. The very meaning of travel would be redefined, becoming not just a change in location but a journey between distinct laws of physics. It's a concept that blurs the lines between science and sheer fantasy, yet it emerges from serious attempts to understand the implications of general relativity when combined with quantum mechanics and the inflationary model of the early universe. The theoretical models supporting this idea often involve highly complex geometries and extreme conditions. For instance, some theories suggest that a black hole in one universe could lead to a white hole in another, with the wormhole acting as the connecting conduit. In this scenario, matter falling into a black hole in our universe might not be destroyed but rather recycled and expelled into a new, parallel universe through a white hole. This would mean that the death of a massive star in one universe could be the birth of a new universe, or at least a new cosmic region in another. Such a process could establish a continuous cycle of creation and destruction across the multiverse, with wormholes serving as the cosmic umbilical cords. However, the challenges to this concept are even greater than those for interstellar wormholes within our own universe. The stability requirements for a wormhole connecting different universes would be even more stringent, likely demanding the precise manipulation of colossal amounts of exotic matter or other as yet undiscovered forms of energy. Furthermore, the very existence of parallel universes is still a subject of intense debate, remaining firmly in the realm of theory and mathematical speculation. There is currently no observable evidence to suggest that such parallel universes exist, let alone that wormholes could connect them. Yet, the allure of inter-universal travel through wormholes remains a captivating frontier of theoretical physics, pushing the boundaries of what we can imagine about the universe or universes we inhabit. It suggests that the deepest secrets of reality might lie not just in exploring the vastness of our own cosmos, but in uncovering the hidden pathways to an infinite cosmic tapestry. While we ponder the grand cosmic shortcuts between universes, let's zoom in far beyond what our most powerful microscopes can see, to a realm where space-time itself behaves in astonishing, almost liquid-like ways. This brings us to a revolutionary concept known as quantum foam, initially proposed by the visionary physicist John Wheeler in the 1950s. Wheeler, a close collaborator of Albert Einstein, grappled with the profound implications of quantum mechanics when applied to the very fabric of space-time. His radical idea suggests that at incredibly tiny scales, specifically at the Planck length and Planck time, the smallest meaningful units of distance and time in physics, the smooth, continuous space-time we experience at macroscopic levels breaks down into a tumultuous, frothing sea of fluctuating geometries. Imagine, if you will, the surface of a seemingly calm ocean. From afar, it looks smooth and flat, but as you get closer, you start to see ripples, then waves, and if you zoom in even further, you'd find a chaotic, turbulent motion of individual water molecules constantly forming and dissipating. Quantum foam is a similar idea but applied to space-time itself. At the Planck scale, space-time isn't smooth and well-behaved. It's constantly bubbling, twisting, and contorting, forming myriad fleeting, transient wormholes and other exotic topologies. These mini wormholes are not stable structures that persist for any meaningful duration. Instead, they spontaneously pop into and out of existence, driven by the inherent uncertainty principles of quantum mechanics. It's a dynamic, seething mass where the laws of classical general relativity cease to apply and quantum effects dominate. These quantum foam wormholes are incredibly tiny. We're talking about dimensions smaller than an atom by many, many orders of magnitude. For perspective, if an atom were expanded to the size of the observable universe, a Planck length would still be smaller than a single tree on Earth. So, these wormholes are utterly microscopic, far too small for anything we can imagine to traverse. They exist as ephemeral quantum fluctuations, mathematical constructs that emerge from attempts to unify gravity with quantum mechanics. However, despite their fleeting nature and minuscule size, their theoretical existence is crucial for understanding the potential role of wormholes in the grander scheme of quantum gravity. The primary role of these quantum foam wormholes is tied to the very nature of quantum gravity itself. One of the biggest challenges in theoretical physics is reconciling general relativity, which describes gravity and the large-scale structure of the universe, with quantum mechanics, which describes the behavior of matter and energy at the subatomic level. At ordinary scales, these two theories work perfectly well in their respective domains. But when you try to apply quantum mechanics to space-time at the Planck scale, you encounter inconsistencies and infinities. The quantum foam concept provides a theoretical framework where space-time itself is quantized and fluctuating, allowing for the possibility of a unified theory. These mini wormholes become an inherent feature of space-time at its most fundamental level, representing the gravitational equivalent of quantum fields that constantly fluctuate and interact. Furthermore, quantum foam wormholes play a critical role in the information exchange within the universe at these ultra-small scales. While not traversable in a macroscopic sense, they could theoretically act as conduits for quantum information, potentially influencing phenomena like quantum entanglement or even the flow of time at its most fundamental level. Some theories suggest that the noise or fuzziness of quantum foam could contribute to decoherence, the process by which quantum systems lose their quantum properties and begin to behave classically. In essence, they are the background static of the universe, the constant, chaotic churn that underpins the smooth reality we perceive. Proving the existence of quantum foam and its inherent wormholes is an immense challenge, as their scale makes direct observation impossible with current technology. However, indirect evidence might one day come from incredibly precise measurements of space-time at its very smallest scales, or through their potential influence on phenomena like cosmic rays or gravitational waves. The concept of quantum foam and its embedded wormholes offers a vivid, if abstract, picture of space-time as a vibrant, living entity, constantly shifting and fluctuating, a profound testament to the universe's inherent quantum strangeness. While quantum foam suggests space-time is turbulent at the smallest scales, and exotic matter offers a way to stabilize large wormholes, another fascinating theory posits that wormholes could arise from truly colossal, yet infinitesimally thin, defects in space-time itself, cosmic strings. This concept, emerging from the realm of theoretical cosmology and particle physics, suggests that if such cosmic strings exist, they could warp space-time in such a profound and peculiar way as to naturally create shortcuts without the need for elusive exotic matter. To understand cosmic strings, imagine the early universe just moments after the Big Bang. As the universe expanded and cooled, it underwent a series of phase transitions, much like water freezing into ice. During these transitions, some theories predict that topological defects, akin to cracks or imperfections in a crystal, could have formed in the fabric of space-time. These defects are cosmic strings. They are not made of matter in the conventional sense, but are extremely thin, one-dimensional lines of incredibly dense energy, stretching across vast cosmic distances. A single cosmic string, a mere fraction of the width of an atomic nucleus, could be more massive than an entire galaxy. They are remnants of the universe's infancy, relics of a time when fundamental forces were unifying. Now, how could these incredibly thin, incredibly massive objects create wormholes? The key lies in their immense gravitational pull. unlike ordinary matter, which creates a spherical gravitational field around it, a cosmic string's gravity is highly peculiar. Imagine stretching a sheet of rubber. A mass placed on it creates a simple dip. A cosmic string, however, would create a conical shape in space-time around it. If you were to walk around a cosmic string, you'd find that you've effectively traveled less than 360 degrees to return to your starting point, as if a wedge of space-time has been removed, creating a deficit angle. This peculiar warping of space-time means that cosmic strings could act like gravitational lenses, bending light in characteristic ways, but also, more radically, they could create shortcuts. Richard Gott, a prominent astrophysicist, extensively explored the implications of cosmic strings in the 1990s, particularly their potential for time travel and wormhole formation. Gott's work showed that the extreme gravitational effects of two parallel cosmic strings moving past each other at nearly the speed of light could theoretically create closed time-like curves, essentially allowing for backward time travel. While this doesn't directly describe a traversable wormhole in the traditional sense, it hints at the extreme space-time distortions these objects can generate. More directly related to wormholes, other theoretical models suggest that if a cosmic string happened to loop back on itself, or if two cosmic strings came close enough, their combined gravitational fields could pinch off a region of space-time, forming a wormhole. This would be a wormhole formed not by the artificial manipulation of space-time with exotic matter, but by the natural, albeit extreme, gravitational effects of these primordial defects. The beauty of this theory is that it doesn't rely on the creation or manipulation of exotic matter. The wormholes would be a natural consequence of the existence of cosmic strings themselves. The strings would intrinsically possess the unique gravitational properties needed to warp space-time in the required way. However, despite their theoretical elegance, cosmic strings remain hypothetical. Scientists are actively searching for evidence of their existence through their gravitational lensing effects on distant galaxies or through their potential imprint on the cosmic microwave background radiation. No definitive proof has yet been found, but the search continues. If cosmic strings are ever detected, it would not only confirm a major prediction of early universe cosmology, but also open up the astonishing possibility that the very early universe itself laid the groundwork for cosmic shortcuts, etched into the fabric of space-time by these unimaginably thin, ancient threads, forming a natural, albeit accidental, cosmic tunnel. While the physical existence and stabilization of wormholes remain intensely debated, their theoretical implications plunge us into one of the most mind-bending and paradoxical areas of physics: the concept of closed time-like curves, or CTC. If traversable wormholes were real and could be manipulated in certain ways, specifically by moving one of their mouths relative to the other, or placing them in strong gravitational fields, standard general relativity suggests they could allow for journeys not just through space, but through time itself, creating these notorious closed time-like curves. A closed time-like curve is essentially a path through space-time that brings an object or a person back to an earlier point in their own history. Think of it as a loop in time where cause and effect can get tangled in utterly baffling ways. The primary reason why closed time-like curves are so problematic, and why many physicists believe they must be forbidden by the laws of nature, is the array of paradoxes they unleash. The most famous of these is, of course, the grandfather paradox. Imagine for a moment that you enter a wormhole that delivers you to a point in the past before your grandfather met your grandmother. If you then, for whatever reason, prevent their meeting, or worse, somehow cause your grandfather's demise, then your own existence becomes impossible. If you were never born, then you couldn't have traveled back in time to prevent your grandfather's meeting, which means he would have met your grandmother, you would have been born, and the entire logical chain utterly collapses. This kind of paradox isn't just a fun thought experiment for science fiction writers. It strikes at the very heart of causality, the fundamental principle that an effect cannot precede its cause. If CTCs are allowed, causality, as we understand it, breaks down completely. Another equally unsettling paradox associated with closed time-like curves is the information paradox or the self-causation paradox. Imagine a scenario where you send a message through a CTC to yourself in the past, giving yourself a crucial piece of information that you then act upon. Where did that information originate? It seems to have no external source. It simply came into existence within the loop. This creates an uncaused cause, a piece of information that exists without ever being created, or a bootstrap paradox where an object or information exists without ever being originated. For example, if you were to travel back in time and give a young Isaac Newton a completed copy of his Principia Mathematica, then where did the original Principia come from? It would exist without ever having been written. These paradoxes suggest that if CTCs were physically real, the universe would become a chaotic, illogical place, and the deterministic nature of physics, which relies on predictable cause and effect relationships, would crumble. Given these profound logical inconsistencies, physicists have proposed several theoretical solutions or chronology protection mechanisms to prevent the formation of closed time-like curves and safeguard causality. One of the most prominent of these is Kip Thorne's self-consistency principle, sometimes referred to as Novikov's self-consistency principle after Igor Novikov, who also contributed significantly to this idea. This principle suggests that if time travel were possible, any actions taken by a time traveler would inherently be consistent with the past. In other words, you couldn't actually change the past because any attempts to do so would inevitably lead to an outcome that is already part of history, or that simply reinforces the known timeline. So, in the grandfather paradox scenario, if you travel back to try and stop your grandfather, you would somehow fail in your attempt, or your actions would inadvertently ensure their meeting. Perhaps you accidentally introduce them, or your presence as a time traveler scares him into meeting the right person. The universe would conspire, in a sense, to prevent any genuine paradox from occurring. Another proposed solution involves the role of quantum mechanics. At the quantum level, uncertainty reigns, and events are often described in terms of probabilities rather than certainties. Some theories suggest that as you approach a closed time-like curve, quantum fluctuations would become so intense that they would destroy the wormhole before any paradox could form. This would be a form of chronology protection agency built into the very fabric of space-time, preventing the universe from tying itself into logical knots. The extreme energy densities and quantum effects near the entrance to a CTC would act as a cosmic firewall, preventing any object from completing a journey that would violate causality. This chronology protection conjecture posits that the laws of physics are structured in such a way that they actively prevent the creation of macroscopic closed time-like curves, even if the classical equations of general relativity initially seem to allow them. It implies that the universe has a built-in sensor that prohibits time paradoxes, maintaining a consistent timeline. While these proposed solutions offer a way out of the paradoxes, they also underscore the immense theoretical barriers to using wormholes for time travel. The energy requirements to create and sustain a traversable wormhole are already astronomical, but the additional energy needed to manipulate it in a way that creates a CTC, or the extreme quantum effects that would arise, make the prospect seem even more remote. The debate around closed time-like curves and their resolution remains a vibrant area of research in theoretical physics, pushing the boundaries of our understanding of space, time, and the fundamental nature of reality itself. It forces us to confront the deepest philosophical questions about free will, destiny, and the very structure of causation, reminding us that the universe might uphold its logical integrity in ways we are only beginning to comprehend. While the paradoxes of time travel and the need for exotic matter present formidable hurdles for wormholes in general relativity, a fascinating alternative perspective emerges from a completely different approach to quantum gravity, loop quantum gravity. This theory, unlike string theory, doesn't add extra dimensions or fundamental strings. Instead, it proposes that space-time itself isn't a smooth, continuous fabric, but rather a discrete, granular structure like a finely woven mesh. At the incredibly tiny Planck scale, space is made up of fundamental loops or atoms of space, and time flows in discrete steps. This granular nature might just provide a natural mechanism for wormholes to exist without the need for that elusive, theoretical exotic matter, offering a potential loophole around some of the biggest problems. To truly grasp this, imagine zooming in on the fabric of a fine silk scarf. From a distance, it looks perfectly smooth, but up close, you see individual threads woven together, creating tiny loops and knots. Loop quantum gravity suggests space-time is like this, but woven from quantum threads. These threads or loops are the fundamental excitations of the gravitational field. They carry quantum information about the geometry of space-time. As these loops intertwine and connect, they form a network, a spin network, which represents the quantized structure of space. Time in this model emerges from the evolution of these spin networks. This granular structure fundamentally alters our understanding of space-time, moving away from the continuous canvas of general relativity to a quantized, pixelated reality. Now, how does this granular space-time accommodate wormholes, especially without exotic matter? The conventional problem with wormholes is that their throats tend to pinch off and collapse because of the strong gravitational forces. Exotic matter's negative energy density is needed to counteract this. However, in loop quantum gravity, the very quantization of space-time might prevent such a catastrophic collapse. At incredibly small scales, the quantum nature of gravity itself could exert a repulsive force, effectively preventing space-time from being squeezed to an infinitely small point. Think of it like trying to crush a sponge completely flat. At some point, the inherent structure of the sponge resists further compression. Similarly, the atoms of space in loop quantum gravity might resist collapsing beyond a certain point, providing a natural, repulsive effect that keeps the wormhole throat open. The renowned theoretical physicist Carlo Rovelli, one of the pioneers of loop quantum gravity, has explored this very idea. His work suggests that the extreme curvature and density at the center of black holes or within the throat of a wormhole would not lead to an infinite singularity. Instead, due to the quantum nature of space-time, the collapse would bounce at the Planck scale, transitioning into another region of space-time. This quantum bounce could effectively turn what would classically be a singularity into a momentary bridge, a non-singular wormhole. This means that a wormhole would not require exotic matter to counteract collapse, but rather, its stability would be an inherent property of space-time's quantum structure itself. The quantum effects at the smallest scales would naturally provide the stiffening needed to maintain a connection, offering a truly elegant solution to a long-standing problem. Furthermore, this perspective suggests that wormholes might not be rare artificial constructions, but rather a natural, albeit fleeting, consequence of quantum gravitational phenomena. They could be the result of extreme space-time curvature where the classical description of gravity breaks down, and the quantum nature of space-time takes over, creating a momentary tunnel. This could mean that even black holes, instead of leading to a destructive singularity, might naturally transition into a white hole through a quantum wormhole, as predicted by some loop quantum gravity models. This would provide not only a solution to the wormhole stability problem, but also to the black hole information paradox without invoking new, unobserved forms of matter. If this theory proves correct, it would fundamentally change our understanding of space-time, gravity, and the very possibility of cosmic shortcuts, revealing a universe where wormholes are not just theoretical curiosities, but intrinsic features of its granular quantum reality. While many theories explore wormholes as cosmic shortcuts for travel, others venture into an even more abstract yet incredibly exciting domain: their potential role in advanced computation. This brings us to the profound idea that wormholes, particularly those connected through quantum entanglement, could function as a form of quantum computer, leveraging the very fabric of space-time for instantaneous information processing and communication. This isn't about building a traditional computer that uses wormholes as a data highway. It's about the wormhole itself acting as the computational engine, a concept that arises from the deep connections between quantum mechanics, gravity, and information theory. To appreciate this, remember our earlier discussion about the ER=EPR conjecture, which posits that entangled particles are connected by tiny, non-traversable wormholes. If that hypothesis holds true, it suggests a fundamental link between quantum information and the geometry of space-time. Quantum computers, in their essence, harness the bizarre properties of quantum mechanics, like superposition and entanglement, to perform calculations far beyond the capabilities of classical computers. Superposition allows a quantum bit or qubit to exist in multiple states simultaneously, while entanglement links qubits in such a way that the state of one instantly influences the state of another, no matter the distance. This spooky action at a distance is precisely what makes quantum computing so powerful, enabling parallel processing on an unprecedented scale. Now, imagine if the entangled qubits powering a quantum computer were not just abstract mathematical constructs or physical particles in a laboratory, but were fundamentally connected by the tiny wormholes theorized by ER=EPR. This shifts the paradigm. The wormhole isn't just a metaphor for the connection. It literally is the connection, a geometric manifestation of entanglement. If you could control and manipulate these microscopic wormholes, or the entangled particles they represent, you might effectively be manipulating the very pathways of information flow through space-time at its most fundamental level. This would allow for computational processes that occur not merely through electrical signals moving along wires, but through the intrinsic relationships woven into the fabric of the universe itself. The speculation goes even further. If traversable wormholes could somehow be stabilized, even microscopically, they could potentially enable a form of quantum computation or communication that completely bypasses the limitations of space and time. Imagine placing one entangled qubit on Earth and its partner on a distant planet. If they were connected by a wormhole, the measurement of that entanglement could be interpreted not just as an instantaneous correlation, but as a computational step performed across vast distances. This could lead to a form of distributed quantum computing where components of a computation are physically separated by light years, yet communicate as if they were side by side, achieving truly instant processing regardless of spatial separation. The wormhole in this context becomes the ultimate quantum internet cable, allowing for information to flow instantaneously between widely separated computational nodes, effectively collapsing distances for data transfer. Moreover, some theoretical models suggest that if you could somehow create a network of these tiny, interconnected wormholes, a kind of quantum foam on demand, you might be able to process information in ways that leverage the very curvature and topology of space-time. Instead of digital bits, the computations would involve geometric transformations, where the shape and connections of space-time itself perform the calculation. This is pushing the boundaries of current understanding, but it aligns with a growing school of thought that space-time, gravity, and quantum information are deeply intertwined, perhaps even emergent from one another. In this futuristic vision, the wormhole isn't merely a physical shortcut. It's a computational shortcut, a machine that processes information by bending and connecting the universe, offering a glimpse into a future where the laws of physics are not just observed, but actively leveraged as the ultimate computing substrate. While the sheer scientific marvel of wormholes as potential supercomputers is captivating, let's step back and consider their implications for one of the most profound questions ever pondered by humanity, the Fermi Paradox. This paradox, named after physicist Enrico Fermi, can be boiled down to a simple yet chilling question. If the universe is so vast and life is common, then where is everybody? The cosmos is ancient and immense, filled with billions of galaxies, each with billions of stars. Many of these stars are billions of years older than our Sun, theoretically providing ample time for countless civilizations to have evolved, spread, and become technologically advanced. Given these statistics, the silence is deafening. We haven't found a single definitive sign of intelligent alien life. No signals, no artifacts, no evidence of cosmic megastructures like Dyson spheres. This stark contradiction between the high probability of extraterrestrial intelligence and the apparent lack of evidence for it is the Fermi Paradox, and wormholes offer a truly fascinating, albeit speculative, potential solution. One of the fundamental assumptions in the Fermi Paradox is related to the immense travel times required for interstellar expansion. If civilizations are limited to sublight speeds, even reaching a fraction of the speed of light, exploring and colonizing the galaxy would take millions of years. This slow pace makes it difficult to understand why, given billions of years, no civilization has managed to spread its influence throughout the galaxy. However, if advanced civilizations were able to discover, create, or manipulate traversable wormholes, the entire premise of vast interstellar distances would fundamentally change. If wormholes allow for near-instantaneous travel across light years, then interstellar expansion wouldn't be a slow crawl but an immediate leap. A civilization capable of utilizing wormholes could colonize an entire galaxy not in millions of years but potentially in thousands or even less, effectively shrinking the vastness of space. So, how does this offer a solution to the Fermi Paradox? There are several intriguing possibilities. Firstly, the great filter might lie not in the evolution of life or intelligence, but in the discovery and mastery of wormhole technology itself. Perhaps it is incredibly difficult, dangerous, or energy-intensive to create and stabilize traversable wormholes. If only a tiny fraction of advanced civilizations ever reach this technological stage, then the number of intergalactic travelers would be drastically reduced, explaining our apparent isolation. Civilizations that don't master wormholes might simply remain confined to their star systems, unable to overcome the immense distances to reach us. The filter wouldn't be about whether life exists, but whether that life can literally warp space-time. Secondly, if wormholes are relatively easy to create and utilize once a certain level of technology is reached, then the lack of observable aliens might be explained by the wormhole express lane hypothesis. Perhaps advanced civilizations don't bother with messy, energy-intensive sublight speed travel and visible megastructures. Instead, they use a network of hidden or discrete wormholes, moving between star systems efficiently and unobtrusively. They might not need to convert entire stars into energy-harvesting spheres if they can simply pop into a wormhole and gather resources from many different, distant systems with minimal effort. Their presence would be virtually undetectable to us, as they would leave no visible traces in conventional space. This would mean that the galaxy isn't empty. It's just that advanced civilizations are operating on a completely different scale of connectivity, using pathways we can't yet perceive or access. Thirdly, the use of wormholes could lead to an entirely different kind of galactic society, one that doesn't feel the need for extensive physical colonization. If resources can be accessed from across the galaxy via wormholes, or if virtual realities and digital consciousness become paramount, the drive for physical expansion might diminish. Civilizations might simply live in highly optimized, perhaps even small, habitats, jumping through wormholes to access whatever they need, rather than building vast empires that rely on slow, physical interstellar travel. Their existence would be largely localized, only interacting with the universe through these hidden cosmic gateways, making them invisible to our current search methods. Finally, there's the more unsettling possibility that if wormholes are gateways to other universes, as some theories suggest, then advanced civilizations might simply have left our universe entirely. If a civilization masters inter-universal wormholes, they might have found a more resource-rich, stable, or simply more interesting cosmos to inhabit, leaving behind our humble universe. This would be the ultimate solution to the Fermi Paradox. They're not here because they're literally somewhere else beyond our cosmic horizon. While these wormhole-centric solutions to the Fermi Paradox remain purely speculative, they offer a tantalizing shift in perspective. If wormholes are real, they don't just solve problems of travel. They could fundamentally alter the entire context of alien civilizations and their apparent absence, suggesting that the silence isn't due to a lack of life, but perhaps a radically different, faster, and more discrete mode of cosmic existence. While the Fermi Paradox ponders where everyone is in our three spatial dimensions, other theories suggest that wormholes might be hiding in plain sight, masquerading as something else entirely, because our universe itself is just one slice of a larger, higher-dimensional reality. This brings us to a mind-bending concept particularly explored in models like the Randall syndrome scenario, which posits that our entire four-dimensional universe, the three spatial dimensions we experience plus time, is actually just a brain, a kind of cosmic membrane floating within a larger five-dimensional bulk space. Imagine a fish living on the surface of a pond. It can only perceive two dimensions of space: forward, backward, left, and right on that surface. It has no direct awareness of the third dimension, depth. Even if a bird flies over the pond, the fish would only see its shadow on the surface, a two-dimensional projection of a three-dimensional object. The Randall syndrome model suggests a similar situation for us. We are like the fish, confined to our four-dimensional brain, unable to directly perceive the extra fifth dimension. All the particles and forces we know, except for gravity, are thought to be stuck on our brain. Gravity, however, is unique. It is free to propagate into this extra fifth dimension, leaking off our brain into the bulk. This subtle leakage of gravity away from our brain could explain why gravity appears so much weaker than the other fundamental forces, like electromagnetism or the strong and weak nuclear forces. Now, how does this relate to wormholes? In this five-dimensional bulk space, wormholes could exist as natural features, connecting different points within the bulk, or perhaps even connecting different brains, different universes if there are multiple. If our universe is merely a four-dimensional slice through this five-dimensional bulk, then a wormhole existing in the full five dimensions might appear very differently to us, confined to our four-dimensional brain. What a five-dimensional wormhole looks like when projected onto our four-dimensional space-time could be something entirely unexpected. Specifically, some interpretations suggest that what we perceive as black holes in our four-dimensional universe might actually be the four-dimensional shadow or projection of a five-dimensional wormhole. If a wormhole in the higher dimension extends into our brain, its immense gravitational pull leaking from the bulk could appear to us as a region of extreme space-time curvature, precisely what we call a black hole. So, when we observe a black hole with its intense gravity and event horizon, we might not be looking at a singular point of infinite density, but rather the four-dimensional manifestation of a wormhole mouth opening into a higher dimension. The implications of this are truly profound. If black holes are indeed wormholes in disguise from a higher dimension, it changes their nature entirely. Instead of being cosmic dead ends, they would be gateways. Matter falling into a black hole wouldn't necessarily be crushed at a singularity. It would simply be passing through the four-dimensional mouth of a five-dimensional wormhole, potentially exiting into another region of the bulk, another dimension, or even another brain. This perspective could also help to resolve the black hole information paradox. Information wouldn't be lost, it would simply escape our four-dimensional universe by traversing through the higher dimensional wormhole. Moreover, if our universe is just one brain in a larger bulk, then the concept of wormholes could extend beyond mere black holes. Perhaps there are other types of wormholes, not necessarily appearing as black holes, that connect different points on our brain through the bulk. This would be like folding our four-dimensional brain through the fifth dimension to bring two distant points together. The journey wouldn't involve traversing the large distance on the brain, but rather taking a shortcut through the higher dimension. This could explain phenomena like the apparent uniformity of the cosmic microwave background radiation, or even provide pathways for new fundamental particles to enter our universe from the bulk. However, proving the existence of extra dimensions and whether black holes are indeed their wormhole projections remains a massive challenge. Experimental evidence for extra dimensions is currently elusive, though physicists are searching for their subtle gravitational effects or for particles that might be able to traverse them. If we could detect ultra-small black holes or subtle deviations in gravity at very small distances, it could provide indirect evidence for these higher dimensions. Nevertheless, the idea that wormholes might be an inherent feature of a higher dimensional reality offers a compelling and elegant solution to some of the most perplexing mysteries in physics, suggesting that the universe is far richer and more interconnected than our four-dimensional perception currently allows us to grasp. While the idea of wormholes emerging from extra dimensions is highly theoretical, another compelling hypothesis brings the concept much closer to observable astrophysical phenomena, the violent collision of black holes. Recent breakthroughs in numerical relativity, the branch of physics that uses computer simulations to solve Einstein's equations, suggest that the spectacular merger of two black holes might momentarily create wormhole-like structures. This isn't about stable, traversable shortcuts, but rather a fleeting, dynamic warping of space-time that momentarily resembles a wormhole during one of the universe's most catastrophic events. To understand this, let's consider the incredible power released when two black holes spiral inward and finally merge. These events are so energetic that they literally shake the fabric of space-time, producing ripples known as gravitational waves. The first direct detection of these waves in 2015 by the Laser Interferometer Gravitational Wave Observatory, or LIGO, opened up a new window to the cosmos, allowing us to hear the universe's most violent cosmic dances. As two black holes orbit each other, they draw closer and closer, accelerating to incredible speeds. In the final moments before they coalesce into a single, larger black hole, the space-time around them becomes incredibly distorted and turbulent. The gravitational fields are so intense and dynamic that they stretch, twist, and deform space-time in ways that defy everyday intuition. It's within these extreme, dynamic conditions that numerical relativity simulations have hinted at transient wormhole formations. These simulations solve Einstein's complex equations on supercomputers, painstakingly calculating how space-time evolves during a black hole merger. What they've shown is that during the final plunge and coalescence, the single event horizon of the newly formed black hole doesn't just smoothly form. Instead, for a brief flicker of time, the geometry of space-time can become so convoluted that it forms a bridge or tunnel before settling into a more stable configuration. This bridge acts like a momentary wormhole, connecting different regions of the incredibly strained space-time around the merging black holes. It's not a tunnel to another galaxy, but a highly dynamic and short-lived connection within the immediate vicinity of the merger. Think of it like this. Imagine two massive whirlpools spinning side by side, drawing water inward. When they finally collide and merge into one super whirlpool, there's a moment of immense turbulence where the water might briefly form unusual vortex connections or temporary tunnels before stabilizing. In the case of black holes, it's space-time itself that is swirling and collapsing. These simulated wormhole-like structures are often referred to as geodesic bridges or space-time tunnels because they represent paths that particles could theoretically take through the violently warped region, effectively being spat out from one mouth to another if they happen to enter at precisely the right fleeting moment. They are not stable, and they would collapse almost as soon as they form, making them utterly useless for any kind of purposeful travel. The significance of these findings lies not in their practical application for space travel, but in their theoretical implications. If such wormhole-like geometries can spontaneously arise, even fleetingly, during black hole mergers, it suggests that wormholes are not just abstract mathematical constructs requiring exotic matter, but could be natural, albeit ephemeral, features of extreme space-time dynamics. It implies that the universe, in its most violent convulsions, might naturally generate these topological shortcuts. Furthermore, the study of these transient wormholes could provide crucial insights into the ultimate fate of matter falling into black holes and the very nature of singularities. If gravitational waves are the direct observable consequence of black hole mergers, then perhaps subtle signatures of these momentary wormhole formations could one day be imprinted on the gravitational wave signals themselves, offering an indirect way to probe these bizarre spacetime configurations. While direct observation of these fleeting wormhole structures remains impossible, the detailed numerical simulations offer a glimpse into the universe's most extreme gravitational gymnastics, suggesting that wormholes might be a more intrinsic, if brief, part of cosmic reality than previously imagined, born from the spectacular death throes of the largest stars. While the universe's most violent events might momentarily give rise to wormhole-like structures, another profound theoretical puzzle has driven physicists to consider wormholes as a potential solution: the black hole information paradox. This paradox, perhaps one of the most vexing problems in modern physics, highlights a fundamental conflict between two of our most successful theories: Albert Einstein's general relativity and the principles of quantum mechanics. At its core, the black hole information paradox asks a deceptively simple question: what happens to the information of everything that falls into a black hole? According to general relativity, anything that crosses a black hole's event horizon, be it a star, a planet, or even a single subatomic particle, is irrevocably lost to the outside universe. It appears to plunge towards an infinitely dense singularity, and all its unique properties, its information like its precise quantum state, its spin, its charge, its chemical composition, seem to be destroyed. This is akin to burning a book. While the book is destroyed, the information contained within its pages isn't truly gone. It's simply encoded in the smoke, ash, and heat. In physics, the concept of information is much more fundamental than just the words on a page. It refers to the precise quantum state of every particle, which, according to quantum mechanics, should be conserved. However, in the 1970s, the brilliant physicist Stephen Hawking deepened the mystery with his groundbreaking discovery of Hawking radiation. Hawking showed that black holes aren't entirely black. They slowly evaporate over incredibly long periods by emitting a faint thermal radiation from just outside their event horizons. This radiation carries no information about what fell into the black hole. It's purely thermal, like heat from a stove. This implies that as a black hole evaporates, it simply vanishes, leaving behind nothing. All the complex information about the matter that formed it, and everything that subsequently fell into it, would be utterly lost from the universe. This directly contradicts a fundamental principle of quantum mechanics: that information can never be truly destroyed. If information is lost, it violates a concept known as unitarity, which is central to how quantum mechanics describes the evolution of physical systems. It would be like having a magic trick where the magician not only makes the rabbit disappear, but also makes it so that you can never, ever figure out anything about the rabbit that was there. The stakes of this paradox are enormous. If information is indeed destroyed in black holes, it means that our universe is not truly deterministic at its most fundamental level, or that quantum mechanics as we understand it is incomplete. It's a crisis at the very foundations of physics. This is where wormholes enter the picture as a potential savior of information. Instead of matter being crushed to oblivion at a singularity, or its information being lost to the cosmos, the idea is that black holes might not contain singularities at all, but rather wormholes. If the interior of a black hole doesn't lead to a destructive singularity, but instead connects to a wormhole, then the information would not be lost, it would simply be rerouted. The wormhole would act as a cosmic bypass, preserving the information by connecting the black hole's interior to another region of space-time. This other region could be a distant part of our own universe, a white hole acting as an exit, or even a separate parallel universe. The information would simply pass through this cosmic tunnel, emerging somewhere else, albeit potentially in a highly scrambled or unrecognizable form. This would mean that the black hole functions as a kind of cosmic information redistribution center rather than a cosmic shredder. One specific model that attempts to resolve the information paradox using wormholes is the idea of ER equals EPR that we discussed earlier, where quantum entanglement is equivalent to a wormhole. If matter falling into a black hole becomes highly entangled with the Hawking radiation it emits, then the wormhole connection between the black hole's interior and the outgoing radiation could preserve the information. The information isn't gone, it's simply encoded in the entanglement between the black hole remnant and the radiation that has left it. This suggests a deep, geometric connection between information and the very fabric of space-time, where the wormhole acts as the physical manifestation of that quantum link. Furthermore, some theories propose that black holes might tunnel into white holes through a wormhole, preserving information. For example, in loop quantum gravity, the singularity inside a black hole might naturally bounce into a white hole due to quantum effects, creating a non-singular wormhole connection that effectively channels the information through. This would mean that black holes are not endpoints of information, but rather conduits, continually recycling the universe's content by providing a pathway to other regions or even other universes. The information would never truly be destroyed, just passed along through this cosmic plumbing system. The resolution of the black hole information paradox is considered one of the holy grails of theoretical physics, and wormholes offer one of the most compelling, albeit speculative, pathways to that resolution. If wormholes are indeed the key, it would fundamentally change our understanding of black holes from destructive cosmic monsters to complex, information-preserving entities that connect vast regions of space-time, acting as cosmic librarians rather than cosmic incinerators. This perspective not only solves a deep theoretical puzzle, but also paints a much more interconnected and information-rich picture of the universe, where even the most extreme gravitational objects serve an integral role in the cosmic dance of information. While wormholes offer a fascinating solution to the black hole information paradox, another highly speculative yet intriguing theory ventures into their potential role in understanding one of the universe's most elusive mysteries, dark matter. This concept proposes that some dark matter, the invisible substance making up about 27% of the cosmos, might not be a new, exotic particle, but rather ordinary matter that is simply flowing through a network of tiny, primordial wormholes, creating observed gravitational anomalies without emitting or reflecting light. To grasp this idea, let's briefly recall the puzzle of dark matter. Astronomers first inferred its existence by observing the rotation curves of galaxies. Stars on the outer edges of spiral galaxies were orbiting much faster than they should have been, given the amount of visible matter. It was as if there was extra, invisible mass providing the gravitational pull to keep these stars from flying off into space. This discrepancy, observed in galaxies, galaxy clusters, and even the large-scale structure of the universe, led to the conclusion that a significant portion of the universe's mass is made up of something we cannot see or directly detect. Despite decades of searching, no candidate for this dark matter particle has been definitively found. Various theories suggest dark matter could be made of weakly interacting massive particles, or WIMP, or actions, or even primordial black holes, but none have been confirmed. This is where wormholes offer a radical alternative. Instead of proposing new particles, this theory suggests that the dark matter we observe might simply be ordinary matter that is temporarily residing in a hidden sector of space-time, connected to our universe via a network of microscopic primordial wormholes. Imagine our universe as a vast two-dimensional sheet and another parallel universe, or even just a hidden pocket of our own universe existing on an adjacent sheet. If these sheets were connected by tiny, stable wormholes, matter could periodically leak or flow from one sheet to the other through these cosmic conduits. When this ordinary matter exists on the other side of the wormhole or is in transit through the wormhole itself, it would exert gravitational influence on our universe, but it would be completely invisible to our telescopes because it's not directly interacting with light or electromagnetic forces within our observable space. It's effectively dark to us because it's spatially separated, operating on a different, inaccessible plane. The concept leans heavily on the idea of primordial wormholes, those microscopic tunnels that might have survived from the chaotic, super-dense conditions of the early universe, as we discussed earlier. If these ancient relics exist, they could form a kind of cosmic subway system, silently shuttling matter between different regions of space or even between different universes or dimensions. The gravitational effects of this hidden, flowing matter would manifest as the dark matter we detect. For example, if a galaxy happened to be situated near a particularly dense region of these primordial wormholes, and matter was flowing through them from a hidden reservoir, the galaxy would appear to have more mass than its visible stars and gas account for, perfectly explaining the anomalous rotation curves. Furthermore, this wormhole dark matter hypothesis could potentially explain some of the more puzzling anomalies observed in galactic rotation curves and galaxy clusters. For instance, some observations suggest that dark matter doesn't always cluster in the way standard particle dark matter models predict. If dark matter is instead dynamic, moving in and out of our observable universe through wormholes, it could exhibit different clustering patterns or even subtle variations in its apparent distribution that are difficult to explain with static particle models. It transforms dark matter from an unknown particle into a phenomenon driven by the topology of space-time itself. However, the challenges to this theory are significant. Firstly, it requires the existence and stability of primordial wormholes, which are themselves highly theoretical and unproven. Secondly, it requires a mechanism for ordinary matter to enter and exit these microscopic wormholes, and to do so in a way that generates the precise gravitational profile observed in galaxies. This would imply a continuous, natural process of matter transit through these wormholes, rather than just isolated events. Thirdly, if matter is constantly flowing in and out of our universe through these portals, there might be subtle energetic signatures or effects that we haven't yet been able to detect. Nevertheless, the wormhole dark matter hypothesis offers an incredibly creative and elegant solution to one of cosmology's greatest mysteries. It suggests that the invisible mass permeating our universe might not be made of exotic particles, but of components of our familiar universe that are simply taking a detour through a hidden dimension, accessing our reality only through the gravitational pull of these ancient, pervasive cosmic shortcuts. It paints a picture of a universe where missing mass isn't missing at all, but rather just cleverly concealed, traversing unseen pathways in the fabric of space-time that our current instruments are blind to. While the concept of dark matter flowing through wormholes offers a way to explain unseen mass, another highly advanced and deeply theoretical idea brings us to the very cutting edge of particle physics, the potential role of supersymmetry in stabilizing wormholes. This theory suggests that if supersymmetry, or SUSY, exists, it could provide the natural, exotic matter-like conditions needed to keep a wormhole open, offering a solution without inventing new, unproven substances. Supersymmetry is a theoretical extension to the standard model of particle physics, which is our most successful theory describing the fundamental particles and forces that make up the universe. The standard model explains a vast array of phenomena, but it has limitations. For instance, it doesn't include gravity, and it has some aesthetic issues like the hierarchy problem, which relates to the huge difference between the electroweak scale and the Planck scale. Supersymmetry attempts to address these issues by proposing that for every known particle in the universe, there exists a heavier superpartner. So, for every fermion like electrons and quarks, there's a corresponding boson superpartner, and for every boson like photons and gluons, there's a corresponding fermion superpartner. These hypothetical superpartners haven't been directly observed, which means if they exist, they must be very massive, requiring more energy to create than our current particle accelerators can produce. Now, how does this relate to wormholes? Some of these hypothetical superpartners possess properties that could naturally act like the exotic matter needed to stabilize a traversable wormhole. For example, particles like the neutralino, a hypothetical superpartner of the photon, Z boson, and Higgs boson, are strong candidates for dark matter in some supersymmetric models. More significantly, certain supersymmetric theories predict the existence of particles or fields that inherently have negative energy density under specific conditions. While ordinary matter and energy like visible particles always have positive energy density, some supersymmetric partners, or the quantum fields associated with them, might naturally exhibit the peculiar repulsive gravitational effect required to prop open a wormhole throat. This would mean that the very fabric of space-time could be stabilized by these supersymmetric particles without needing to invent entirely new, exotic forms of matter. Consider the detailed physics of what happens inside a wormhole. The throat of a wormhole exerts immense gravitational pressure that attempts to pinch it closed. To counteract this, you need a substance that exerts a repulsive gravitational force. In general relativity, this translates to matter with negative energy density. While this sounds bizarre, certain quantum field theories, including some versions of supersymmetry, allow for localized regions of negative energy density to exist, albeit often fleetingly or under extreme conditions. If supersymmetric particles are real, and if they can be manipulated or concentrated in specific configurations, their quantum vacuum states or interactions could generate the necessary negative energy. This would be a profound discovery because it would mean that the very solution to the wormhole stability problem is embedded within the fundamental symmetries of nature, rather than requiring an arbitrarily introduced hypothetical substance. The implications for wormhole creation and stability are significant. If nature is indeed supersymmetric, then the universe might already contain the very ingredients needed for traversable wormholes. The challenge would then shift from creating completely alien exotic matter to understanding and harnessing these existing supersymmetric fields or particles. For instance, if experiments at particle accelerators like the Large Hadron Collider were to finally detect evidence of superpartners, it would be a monumental step towards validating supersymmetry and, by extension, open up new avenues for exploring wormhole physics. Such a discovery would fundamentally reshape our understanding of matter and energy, providing a deeper insight into the forces that could potentially manipulate space-time itself. It transforms the problem of wormhole stabilization from inventing an impossible material to discovering a new layer of reality that is already part of the universe's fundamental makeup. This possibility paints an elegant picture where wormholes aren't just theoretical constructs, but a natural, albeit extremely difficult to achieve, consequence of the universe's deeper hidden symmetries. While supersymmetry offers a potential solution for stabilizing wormholes at a microscopic level, let's now consider a truly grand cosmological application for these cosmic tunnels, their theoretical role in the ultimate fate of the universe. This brings us to a fascinating and deeply speculative idea that wormholes could become dominant features of space-time in a collapsing universe, potentially offering escape routes before a hypothetical Big Crunch singularity. To understand this, we need to revisit the potential fates of our universe. For a long time, cosmologists debated whether the universe would expand forever, or if gravity would eventually halt its expansion and pull all matter back together in a catastrophic event known as the Big Crunch. In a Big Crunch scenario, the universe would contract, growing hotter and denser, eventually collapsing back into an infinitely dense hot singularity, a reverse Big Bang. While current observations strongly suggest that dark energy is accelerating the universe's expansion, making a Big Crunch unlikely, it remains a valid theoretical possibility depending on the unknown properties of dark energy and the total mass energy density of the cosmos. If, for instance, dark energy were to weaken or reverse its repulsive effect over cosmic timescales, or if the universe's overall density were subtly higher than currently estimated, a Big Crunch could still be in our unimaginably distant future. Now imagine such a collapsing universe. As space contracts, galaxies draw closer, then stars, and eventually even atoms are squeezed together under unimaginable gravitational pressure. The density and curvature of space-time would become extreme, far surpassing anything we currently observe. It's in this hyper-dense, hyper-curved environment that some theorists speculate wormholes could become not just possible but potentially prevalent, dominating the very geometry of space-time. As the universe nears its final, fiery collapse, the conditions would resemble those of the early universe or the interiors of black holes, environments where wormholes are theorized to naturally form or become stable. The extreme energies and densities could inherently warp space-time in ways that favor the creation and maintenance of these cosmic tunnels. The idea here is that as space-time becomes increasingly curved and compact, the distance between any 2 points effectively shrinks. If the universe were to contract to a size where quantum gravitational effects become dominant, the quantum foam that we discussed earlier could become much more pronounced, with larger and more stable wormholes spontaneously forming. These wormholes, born from the extreme conditions of universal collapse, might not require exotic matter because the universe itself would be providing the necessary extreme negative pressure or curvature throughout its fabric. The very geometry of a collapsing space-time could inherently be wormhole-rich. The most dramatic implication of this theory is the possibility of escape routes from the Big Crunch. If these wormholes become widespread and stable enough in the final moments before singularity, a highly advanced civilization could, in theory, utilize them to escape the collapsing universe. These wormholes wouldn't just be shortcuts within the universe, they would be literal escape hatches from the universe itself. They could lead to another universe, perhaps one that is expanding, or a newly formed baby universe that buds off from the collapsing parent. It implies a cosmic recycling mechanism where the Big Crunch isn't an absolute end but a gateway to new beginnings. This concept is often tied to the idea of a cyclic universe, where a Big Crunch is followed by a Big Bang, or even a more intricate multiverse, where collapsing universes seed new ones through these wormhole conduits. The wormholes would act as cosmic lifeboats, allowing information or even beings to tunnel out of a dying universe and emerge into a fresh, expanding cosmos. However, the scientific hurdles for this Big Crunch wormhole scenario are immense. Firstly, it relies on the Big Crunch happening, which is currently disfavored by observational data regarding dark energy. Secondly, even if it were to occur, the conditions would be so extreme that navigating or even perceiving these wormholes would be unimaginably difficult. The tidal forces would be immense, and the energy requirements for any such escape would be staggering. Thirdly, the very nature of such an escape implies a connection to another space-time, which falls into the realm of multiverse theories, themselves highly speculative. Nevertheless, the idea offers a poetic, almost mythological, solution to the ultimate demise of the universe. Instead of a desolate, final collapse, wormholes present a glimmer of hope for cosmic continuity, a profound testament to the flexibility of space-time, suggesting that even in its ultimate moments, the universe might bend and fold to offer a pathway to new existence. It transforms the final breath of the cosmos into a potential gateway to infinite cosmic rebirth. While wormholes offer a theoretical path to interstellar travel, they are not the only fantastical mechanism proposed for faster-than-light journeys. Another captivating concept, gaining significant attention in science fiction and theoretical physics alike, is the Alcubierre warp drive. This brings us to a fascinating intersection. How do these two mind-bending ideas, wormholes and warp drives, relate? And what do their shared reliance on space-time manipulation tell us about the future of cosmic exploration? The Alcubierre warp drive, proposed by Mexican theoretical physicist Miguel Alcubierre in 1994, doesn't involve traversing a tunnel through space-time. Instead, it suggests a way to essentially fold space-time around a spacecraft, allowing it to travel faster than light without actually breaking the universal speed limit locally. Imagine a starship placed within a warp bubble, a region of space-time that is flat inside, allowing the ship to remain stationary or move at sublight speeds within its immediate vicinity. The ingenious part is what happens outside this bubble. The Alcubierre metric describes a way to contract space-time in front of the bubble and expand space-time behind it. It's like placing a rug on the floor and then pulling the rug forward, effectively carrying the ship along with the distorted space. The ship itself isn't accelerating to superluminal speeds. Rather, the space around it is contracting and expanding, carrying the ship along for the ride. From the perspective of an outside observer, the ship would appear to be moving at many times the speed of light, simply because the space itself is being moved. This is the crucial distinction. The ship isn't locally exceeding the speed of light, so it doesn't violate Einstein's theory of special relativity, which states that nothing can travel faster than light through space. Instead, it manipulates space itself. Now, how do wormholes and warp drives compare, given their shared ambition of faster-than-light travel? Both concepts are deeply rooted in Albert Einstein's general theory of relativity, which allows for the manipulation and distortion of space-time. They both represent highly speculative solutions to the immense distances in the cosmos. However, their mechanisms differ profoundly. A wormhole is a shortcut, a tunnel through space-time that brings two distant points together. It's like folding a piece of paper and punching a hole through it. A warp drive, on the other hand, is more akin to surfing on a wave of distorted space-time, riding a localized distortion that carries the ship along. It doesn't create a tunnel, but rather compresses the space ahead and expands the space behind. So, while a wormhole might allow you to instantly jump from one point to another, a warp drive would allow you to travel continuously, albeit at superluminal effective speeds from point A to point B. The most significant and daunting challenge common to both wormholes and warp drives lies in their energy requirements, and specifically the type of energy they demand: negative energy. As we discussed with traversable wormholes, Kip Thorne demonstrated the need for exotic matter with negative energy density to hold the wormhole throat open and prevent it from collapsing. The Alcubierre warp drive faces a nearly identical hurdle: the space-time distortion required to create a warp bubble. The contraction of space in front and expansion behind also necessitates the presence of negative energy density. Without this exotic energy, the warp bubble simply cannot be maintained. The problem is that negative energy density is not only incredibly difficult to produce but theoretically requires a violation of certain energy conditions in classical physics, making its existence outside of very specific quantum phenomena highly questionable. Furthermore, the sheer amount of negative energy required for a human-scale, practical warp drive is astronomical. Initial calculations for an Alcubierre drive suggested energy demands equivalent to the mass energy of an entire Jovian planet or even a galaxy, compressed into a tiny region, a quantity far beyond any current or foreseeable technological capability. While some theoretical refinements have reduced these energy requirements, they still remain immense, often requiring quantities of negative energy that are many orders of magnitude greater than what we can currently produce, even in microscopic, fleeting quantum fluctuations. So, both wormholes and warp drives depend on our ability to harness or create quantities of negative energy that are currently beyond our grasp and potentially even inconsistent with known physics. Despite these immense energy hurdles, the theoretical parallels between wormholes and warp drives are striking. They both represent creative attempts to leverage the flexibility of space-time predicted by general relativity to overcome the light-speed barrier, not by breaking it but by circumventing it. They push the boundaries of what is possible, suggesting that the universe might have loopholes to interstellar travel embedded within its very fabric, if only we can figure out how to exploit them. The ongoing theoretical research into both concepts continues to inspire and inform our understanding of general relativity, quantum mechanics, and the elusive nature of exotic matter. Even if these direct applications never materialize, the pursuit of these ideas forces physicists to delve deeper into the fundamental laws of the universe, uncovering new insights into the intricate dance between matter, energy, and space-time itself, pushing the frontiers of science in ways that are truly out of this world. While wormholes and warp drives represent theoretical feats of space-time engineering, another, even more radical concept positions wormholes not as mere travel conduits, but as fundamental components of reality itself, inextricably linked to the idea that our universe might be a hologram. This brings us to a profound and mind-bending theory, the notion that wormholes could function as holographic screens, projecting our three-dimensional reality from a two-dimensional boundary. It's a theory that challenges our most basic perceptions of what is real, suggesting that the universe we inhabit might be a cosmic illusion, a detailed projection from a distant, flat surface. This incredibly bold idea draws its roots from the black hole information paradox, as physicists grappled with the idea that information might be lost when it falls into a black hole. Leonard Susskind and Gerard T. Hooft proposed a revolutionary concept known as the holographic principle. They realized that the information about everything that falls into a black hole doesn't seem to depend on the volume of the black hole, but rather on its surface area, specifically the area of its event horizon. This was a startling revelation, as it implied that all the information contained within a three-dimensional volume could be fully encoded on a two-dimensional surface. It's like saying everything inside your living room could be completely described by the patterns on its walls, without needing to know anything about the volume within. This seemed to defy common sense, and yet it was a powerful mathematical insight. The holographic principle then expanded from black holes to the entire universe. If the information of a three-dimensional volume can be encoded on a two-dimensional surface, could our entire three-dimensional universe, with all its stars, galaxies, and even ourselves, actually be a holographic projection of information encoded on a distant, two-dimensional boundary? This is the essence of the holographic universe theory. Imagine a complex security hologram on a credit card. It's a two-dimensional image etched onto a flat surface, but when illuminated with the right light, it projects a three-dimensional image into space. Similarly, the holographic universe theory suggests that the universe we perceive might be a detailed, three-dimensional projection of information living on a two-dimensional surface at the very edge of our cosmos, or perhaps even on a cosmic horizon far beyond our view. Now, where do wormholes fit into this incredibly abstract picture? This is where the concept becomes even more fascinating. Recent theoretical work, particularly building on the anti-de Sitter/conformal field theory correspondence AD-S/CFT, has shown that wormholes can play a crucial role in these holographic models. Within this framework, what appears as a wormhole in the higher dimensional bulk space, our perceived three-dimensional universe, can be mathematically represented as a pattern of quantum entanglement on the lower dimensional boundary theory, the two-dimensional surface. So, an ER equals EPR connection, where entanglement is equivalent to a wormhole, isn't just a quirky theoretical equivalence, it's a fundamental bridge within the holographic framework. The wormhole isn't just a tunnel, it's a geometric manifestation of quantum information, allowing entanglement to bridge vast distances within the projected reality. This implies that wormholes might not be something we travel through physically, but rather fundamental constructs that help stitch together the holographic projection. They are the geometric representations of quantum correlations that define the connectivity of our perceived reality. If 2 points in our three-dimensional universe are quantum entangled, the holographic principle suggests they are connected by a wormhole in the underlying bulk space. The wormhole, in this view, is the projection of entangled quantum states onto a higher dimension. It gives a physical, geometric interpretation to the spooky action at a distance that so puzzled Einstein, suggesting that the instantaneous correlations between entangled particles might be taking a shortcut through a wormhole that is part of the machinery of the holographic projection. The implications are truly mind-bending. If wormholes are indeed holographic screens or components of them, then they might be everywhere, constantly forming and dissipating as quantum information gets processed on the boundary. They wouldn't be massive, stable structures that we could ever hope to fly through, but rather dynamic, energetic manifestations of the information currency of the universe. This perspective profoundly reconfigures our understanding of gravity itself. Gravity, in this view, might not be a fundamental force but rather an emergent phenomenon, arising from the entanglement of quantum bits on the holographic screen. The curvature of space-time, the very essence of gravity, would then be a consequence of the way information is projected from the boundary onto our perceived three dimensions. While the holographic principle and its connection to wormholes remain highly theoretical, lacking direct experimental verification, they offer a powerful framework for unifying general relativity and quantum mechanics. By viewing space-time and gravity as emergent properties of a more fundamental quantum information theory, it bypasses many of the inconsistencies that arise when trying to combine these two pillars of modern physics. It suggests that the quest to understand wormholes isn't just about finding cosmic shortcuts, but about unraveling the very nature of reality. It hints that the universe is far stranger and more subtle than we currently grasp, a grand cosmic illusion where wormholes are not just tunnels through space, but the very seams and connections of the holographic fabric that defines our existence. While wormholes challenge our perceptions of space, time, and even the very nature of reality through concepts like the holographic principle, some of the most far-reaching and speculative theories venture into territory that blurs the lines between physics, philosophy, and spirituality, the potential connection between wormholes and consciousness itself. This realm, often considered fringe physics, explores the idea that wormholes might not just be conduits for matter or energy, but perhaps for non-local consciousness or quantum mind phenomena, opening up a universe where the mind is not merely confined to the brain. This theory draws inspiration from several sources, primarily the perplexing nature of consciousness and the strange phenomena of quantum mechanics, particularly entanglement. Consciousness, despite centuries of philosophical and scientific inquiry, remains one of the universe's greatest mysteries. we don't fully understand how a collection of neurons and synapses in the brain gives rise to subjective experience, thoughts, and self-awareness. Some radical theories propose that consciousness is not merely an emergent property of complex brain activity, but something more fundamental, perhaps a non-local phenomenon, or even an aspect of the universe's underlying quantum reality. If consciousness is indeed non-local, meaning it's not strictly confined to a specific location in space and time, then a mechanism is needed for its communication or influence across distances. This is where wormholes enter the picture. If wormholes are indeed the geometric manifestation of quantum entanglement, as suggested by the ER=EPR conjecture, then could they also be involved in the propagation or connection of consciousness? Quantum entanglement, as we know, seems to connect particles instantaneously, regardless of distance. If consciousness has quantum properties, or if the brain somehow leverages quantum processes to generate consciousness, a highly debated but intriguing hypothesis known as quantum consciousness, or orchestrated objective reduction, proposed by Roger Penrose and Stuart Hameroff, then wormholes could provide the necessary fabric for bridging mental experiences across vast distances, or even across time. Imagine consciousness not as a localized event, but as a field that can be channeled or connected through these space-time shortcuts. The idea suggests that if two conscious entities, or two aspects of a single consciousness, were to become entangled, the underlying wormhole connecting them could facilitate a form of telepathy or non-local awareness. This isn't about sending information through the wormhole in a traditional sense, but about the wormhole representing a direct connection or identification between two seemingly separate conscious nodes. For example, some proponents of this theory speculate that near-death experiences, where individuals report out-of-body sensations or a connection to a universal consciousness, might be explained by a momentary quantum entanglement of the brain with a larger cosmic consciousness, facilitated by fleeting microscopic wormholes. Similarly, phenomena like intuition, premonitions, or collective unconscious experiences could be interpreted as subtle information leaks through these consciousness-bridging wormholes. Furthermore, some very speculative interpretations extend this to the concept of a universal consciousness, or cosmic mind, where wormholes could be the conduits through which individual consciousnesses are connected to or emerge from a larger, overarching awareness. This aligns with certain philosophical and spiritual traditions that view reality as fundamentally interconnected, with individual minds being aspects of a greater whole. In this view, wormholes would be the physical, geometric realization of this interconnectedness, allowing consciousness to transcend its individual, localized boundaries. They would represent the underlying architecture of a universe where mind is not just a biological byproduct, but an integral, perhaps even primary, feature woven into the fabric of space-time itself. The challenges to this theory, however, are immense and span across scientific and philosophical domains. Firstly, consciousness itself is poorly understood, and the idea of quantum consciousness lacks definitive empirical evidence. While there are intriguing correlations directly linking specific quantum phenomena to the observable properties of consciousness remains elusive. Secondly, even if quantum consciousness were proven, the leap from quantum entanglement to macroscopic wormholes that can mediate conscious connections is a massive one, requiring many unproven assumptions about the nature of space-time at extremely small scales and how it interacts with conscious processes. The very definition of information in this context becomes blurred, extending beyond measurable physical quantities to include subjective experience. This theory largely resides in the realm of theoretical speculation and philosophical inquiry rather than testable physics. It's often discussed in contexts that integrate quantum mechanics with Eastern mysticism or panpsychism, the idea that consciousness is a fundamental property of matter. While it lacks empirical support and often steps beyond the boundaries of falsifiable science, It highlights the profound conceptual space that wormholes open up when considering the most fundamental aspects of existence. It pushes our understanding of the universe not just as a collection of particles and forces, but as a potentially interconnected tapestry where even the most elusive phenomena like consciousness might find a geometric home within the mysterious folds of space-time, suggesting that the ultimate frontier of exploration might not be distant galaxies, but the very depths of the mind itself, connected through unseen cosmic tunnels. While some theories explore how wormholes might bridge consciousness or offer pathways across vast cosmic distances, let's conclude our mind-bending journey with perhaps the wildest, most audacious idea of all, that our entire universe, with all its galaxies, stars, and life, might itself be the product of a wormhole born from a black hole in a parent universe. This concept, known as cosmological natural selection, or fecund universes, was proposed by the brilliant theoretical physicist Lee Smolin in the 1990s, offering a startling new perspective on the origin and evolution of the cosmos. Smolin's theory attempts to answer a profound question: why are the fundamental constants of our universe, like the strength of gravity, the mass of electrons, or the speed of light, so perfectly tuned to allow for the formation of stars, galaxies, and eventually life? This is often called the fine-tuning problem. If these constants were even slightly different, the universe would be a barren, lifeless place. Smolin suggests that this fine-tuning isn't a cosmic accident or divine intervention, but rather a result of a process akin to biological natural selection, but applied to universes. Here's how the wormhole connection comes in. Smolin proposes that every time a black hole forms in a universe, it acts as a fecund point, a sort of cosmic birth canal that gives rise to a new, baby universe on the other side of the black hole. This new universe would share most, but not all, of the fundamental constants of its parent universe. Imagine a black hole in our universe. As matter collapses into it, instead of leading to a destructive singularity, the extreme gravitational conditions at the core of the black hole cause a Big Bang-like event to occur, spawning a new universe. This new universe would effectively pinch off from the parent universe, connected by a non-traversable wormhole during its birth. The reason it's non-traversable is that it would essentially snap shut after the birth event, preventing any communication or travel back to the parent. The key to cosmological natural selection lies in the idea of mutations. Each time a new universe is born from a black hole, its fundamental constants might experience slight, random variations or mutations compared to its parent. Universes that produce more black holes are considered fitter in this cosmic evolutionary scheme. Why? Because black holes are the engines of universe reproduction. A universe with constants that favor the formation of many massive stars and galaxies will, therefore, produce many more black holes, and thus many more offspring universes. Conversely, a universe with constants that don't allow for star formation or produce only tiny, short-lived stars would be less fit and produce fewer or no black holes, effectively having fewer descendants. Over countless generations of universes, this process would naturally select for constants that are optimized for black hole production. And here's the brilliant twist: the conditions that are favorable for black hole formation, namely the efficient creation of massive stars, are also, coincidentally, the very conditions that are favorable for the formation of complex structures like galaxies, planetary systems, and ultimately, life. So, the fine-tuning of our universe for life wouldn't be a miracle. It would simply be an emergent property of a universe that is extremely efficient at reproducing itself through black holes. Our universe, in this view, is a descendant of a long lineage of universes that have been optimized through cosmic evolution to be incredibly good at making black holes. And by extension, good at making places where life can arise. This theory offers a grand, sweeping narrative for the origin and evolution of the entire multiverse, where universes are not just born randomly, but inherit and adapt their properties through a process of cosmic fertility. It resolves the fine-tuning problem without invoking supernatural explanations or relying on the sheer luck of a random draw in an infinite multiverse. Instead, it suggests a dynamic, evolving multiverse where the principles of natural selection apply to the fundamental laws of physics themselves. The wormhole, in this context, serves as the ultimate cosmic umbilical cord, linking generations of universes and embodying the reproductive cycle of the cosmos. It transforms black holes from mere devourers of matter into galactic wombs, ceaselessly giving birth to new realities, each subtly different from its parent, in an endless, self-optimizing cycle of cosmic creation. This awe-inspiring idea suggests that wormholes are not just theoretical shortcuts, but the very mechanism of cosmic procreation, hinting that our existence is a fortunate outcome in a grand, evolutionary drama playing out across a vast, interconnected multiverse. And with that astonishing concept, we reach the end of our journey through the 30 most mind-bending theories about wormholes and space-time travel. From the earliest theoretical inklings in Einstein's equations to their potential role in unifying quantum mechanics and gravity, from their paradoxical implications for time travel to their alleged function as cosmic birth canals, wormholes challenge our deepest understanding of reality. They remain firmly in the realm of theory and speculation, demanding the ingenuity of future generations of physicists to unravel their mysteries and determine if these cosmic shortcuts are merely mathematical curiosities or genuine features of a universe far stranger and more flexible than we can currently imagine. The quest continues, leaving us with a profound sense of awe and wonder about the hidden architecture of space, time, and the cosmos itself. And with that astonishing concept, we reach the conclusion of our journey through 30 of the most mind-bending theories about wormholes and space-time travel. We began with Albert Einstein and Nathan Rosen's initial mathematical curiosity, the theoretical bridge that first hinted at cosmic shortcuts. From there, we explored how Kip Thorne and others pushed the boundaries, proposing the necessity of exotic matter to create the traversable wormholes of science fiction. The implications plunged us into the bewildering world of time travel paradoxes, where the universe itself might impose a chronology protection to safeguard causality, preventing those logical inconsistencies that would unravel reality as we know it. Our odyssey then ventured into the deeper quantum realm, where we considered the profound idea that entanglement, that spooky action at a distance, might itself be equivalent to a wormhole, suggesting a fundamental connection between quantum information and the geometry of space-time. This led us to the possibility of primordial wormholes, tiny relics from the Big Bang, perhaps even constituting the mysterious dark matter that pervades our cosmos. We contemplated the dramatic idea that black holes might not be cosmic devourers but instead act as gateways to white holes, or even to new universes through internal wormholes, offering a potential resolution to the vexing information paradox. We then explored how the universe's ultimate structure might inherently include wormholes, especially in the multi-dimensional landscape of string theory, where higher dimensions could provide natural shortcuts, or within the holographic principle, where wormholes emerge as a representation of information projected from a two-dimensional boundary. We dared to connect wormholes to dark energy, the very force accelerating the universe's expansion, suggesting it might be the key to their stabilization. The violent collision of black holes observed through gravitational waves even hinted at fleeting, transient wormhole-like geometries forming spontaneously in the most extreme cosmic events. Our journey also touched upon how loop quantum gravity offers an alternative, non-exotic matter solution for wormholes arising from the granular quantum nature of space-time itself. We mused on their potential as ultimate quantum computers, leveraging the fabric of space-time for instantaneous communication, and considered how their existence might resolve the baffling Fermi Paradox, explaining why we haven't found alien civilizations if they are simply operating on a hidden, wormhole-based network. The idea that our entire universe could be a brain in a multi-dimensional bulk, with black holes acting as higher-dimensional wormhole mouths, expanded our cosmic perspective even further. Finally, the truly audacious concept of cosmological natural selection proposed that our universe might be the offspring of a black hole in a parent universe, with wormholes acting as the reproductive conduits in a grand, evolving multiverse. Each of these theories, in its own unique way, pushes the very boundaries of our understanding of physics, forcing us to reconsider the fundamental nature of space, time, gravity, and reality itself. They demand revolutionary ideas and challenge our most deeply held assumptions. While many remain firmly in the realm of speculation, they are born from serious scientific inquiry, the relentless human quest to decipher the universe's deepest secrets. And as we conclude this mind-bending exploration, one profound question lingers, echoing across the cosmic void. If wormholes truly exist, what's stopping us from finding them? Or perhaps what's stopping them from finding us? We'd love to hear your thoughts on this cosmic mystery. Which of these 30 theories fascinated you the most, or what do you think holds the greatest promise? Share your favorite theory in the comments below, and don't forget to like this video, subscribe to our channel for more cosmic mysteries, and hit that notification bell so you don't miss our next deep dive into the unknown.